By now, I hope you have a basic concept of what it means to have a membrane potential and all the dynamics that are involved in that. Cell membrane being a capacitor, separating charge, creating a voltage potential across the membrane, etc. So what I want to do now is build on that concept of, or build on the concept of membrane potential and move into an action potential. So we're going back to our fictitious cell here. We have our distribution of electrolytes, and we are measuring this cell. So we have empirically determined that the resting membrane potential of this little make-believe cell is at minus 70 millivolts. As I have perhaps mentioned before, the different cell types have different resting membrane potentials. So we're just going to say this one has minus 70 millivolts. So the thing that drives an action potential is the fact that you have a certain configuration of channels within the membrane itself. Not all cell membranes are excitable. And when I say excitable, I'm meaning has the ability to have an action potential. So many cells in your body cannot have action potentials. All cells have a membrane potential, but not all cells can have an action potential. Whether a cell has an action potential is going to be a function of the type of channels that it has within its cell membrane. Of course, we all know that neurons have action potentials. Skeletal muscle fibers have action potentials. Some smooth muscle cells can have action potentials. Okay, so we have plenty that do, but we also have plenty of cell types that don't. And again, it simply depends upon the channels, the nature of the channels that are existing in a cell membrane. Okay, so let's play a little bit because I want to build up to how we get to an action potential. If I'm allowed to vary the nature of the cell membrane itself by thought experiment, opening some channels, closing other channels, we can do this here. So suppose that we have a cell membrane and it has sodium channels, and we're going to find out in a bit that these are voltage sensitive sodium channels, but still, if I had sodium channels that I could open up at will, how would that determine or affect the cell membrane of that cell? So imagine that I'm sitting here at minus 70 millivolts, and we're going to say this is time is moving in that direction there. So I have a resting membrane potential, minus 70 millivolts, so it's in steady state. Again, reminder, it's not in equilibrium, but it's in steady state. And then I go and by just thought, say, let's open up sodium channels. Now, we know from the earlier block that a resting membrane potential of minus 70 millivolts is very far away from the Nernst value of sodium. And again, you can plug in the concentrations of the sodium, 15 in, 145 out, and you find out then that the Nernst value is going to be in the ballpark of plus 70 millivolts. So we're just going to call it, not plus 60 millivolts. So we're just going to assume plus 60 millivolts, close enough. So again, using our loose language that we employed last time, we're going to say that the sodium wants, quote unquote, the membrane to be plus 60 millivolts. So the thing that keeps it from being plus 60 millivolts is the nature of the membrane itself. It's not very permeable to sodium. But if I open up sodium channels, then the membrane becomes much more permeable to sodium. And so let us assume that we're going to open up so many channels that the permeability of the membrane to sodium is ridiculously more than any of the other electrolytes. So it's like 99.9% of the conductance is going to be a function of the sodium. If we do that, and we open up all these sodium channels, and we have them, we keep them open. We don't open them and close them, we keep them open. Then what we would have a rise in the membrane potential. It would quickly go up to near 60 millivolts, and then it would just stay there. So this would then represent the new resting membrane potential. Because remember, we're keeping the sodium channels open. So it would just sit there. So it would just simply zip up to whatever the Nernst value is for sodium. And that's all there is to it. Okay, so let's play the game some more. Let's take a look at potassium. Now what we're doing is resetting the cell. So now we're bringing it back to normal. So now we're still sitting at minus 70 millivolts. That's the resting membrane potential. And now let us say that we're going to open up the potassium channels. Now, as I said in the membrane potential lecture block, the membrane is very permeable to potassium anyway. That's why the resting membrane potential is typically near the Nernst value for potassium. But let's make the cell membrane to be crazy permeable to potassium. So we're going to open up a bunch more potassium channels, and we're going to assume that the Nernst value for potassium is minus 88 millivolts. And again, we're going to find out what happens over time. And of course, you know what's going to happen over time is that the resting membrane potential will go from minus 70, and it will just dip to near minus 88, and that would be my new resting membrane potential. And as long as I kept those potassium channels open, that's where it would sit. Now let's make it even more interesting. Suppose that we say we have a membrane sitting at minus 70 millivolts, that's the resting membrane potential, and we say, okay, let's open up a bunch of sodium channels, and let's open up a bunch of potassium channels, and we're going to make it such that half of the conductance is from sodium and half the conductance is from potassium. So we're going to make the membrane to be equally permeable to both sodium and potassium. What now will happen to the resting membrane potential? So what we have now is the battle of the Nernst values. So we have sodium that wants it at plus 60. We have potassium that wants it at minus 88. But because we're making the membrane equally permeable to both, if you think back to the chord conductance equation, that means we're going to weight the Nernst value of potassium and the Nernst value of sodium at 50%. So they each have half say in where the new resting membrane potential will be. So a couple of ways of looking at this. If we're looking at it in a graphic way, let's do that first, and then we'll plug in our chord conductance because it's going to get you to the same place. Again, we're going to assume that the G for sodium and for potassium are the same. So G for sodium equals for potassium. It doesn't matter what the G is, we just know that they're equal. So we have the battle of the Nernst values. So we have 60 over here, 88 here, and so what I'm interested in now is what is the total units from 60 to minus 88. And if you do the arithmetic, it's going to be 148 millivolts. That's the total span. So then if they're, in a sense, what they're doing is splitting the difference, I would just simply take the 148, I would divide by 2, and that would get me 74. So what that would mean then is that, again, 74 above, 74 below, but I know that splitting that in half is 74. So if I were to half this, roughly around, say, there, so it would be 74 here and 74 here. Well, I would want to know, well, what is that? Well, that's easy enough. You would simply take the 74, and I would add it to the minus 88, and what I would get is going to be minus 14 millivolts. So that figure here is minus 14 millivolts. So now that we know the midline, so if I open both sodium and potassium up at the same time and kept them open, and again, reminder, we're assuming equal permeability. So the membrane potential, I just go a different color for kicks, the membrane potential would go from here, it would go up to plus or minus 14 millivolts, and that would be my new resting membrane potential. Of course, we can do it by the chord conductance. So we would say that the theoretical resting membrane potential is going to equal to 50% of the Nernst value for sodium plus 50% the Nernst value for potassium. And of course, the 50% is 0.5 or 1/2. And recall, how did we get the 50%? Where we got the G potassium over the sum of G sodium over the sum of G. And again, we're assuming here that the only channels we're worried about is sodium and potassium. So if we said that they're equal to each other, then the sum is double. So that would get you your 50%, because these are going to equal to then 1/2, because 1/2 plus 1/2 is, of course, a whole. Well, if you do the arithmetic and then wonder of wonders, the new resting membrane potential is minus 14 millivolts. So that's how that works. Okay, so let's make it even more interesting. Let us say, for kicks, that the sodium, now we're back to normal, we're back to minus 70 millivolt resting membrane potential. And let's suppose that I open up sodium channels first. It's the first thing I do. Then after a certain amount of time, I open up the potassium channels. And then I'm going to let both of them remain open. And again, the end point will be that it's going to be 50-50 in terms of permeability, but I'm messing with the timing of the opening. So what would happen, and again, this depends upon how long I keep things open, so just kind of bear with me on that. So if I open up the sodium channels first, so now I'm heading north. Okay, remember this is time. That direction there. So I'm heading north. So I'm going to go up and up. Now where is it going? It's going towards the plus 60. So it's going to be heading up in that direction there. It will continue up there until I open up the potassium channels. Now as I open up the potassium channels, now that's going to drag it back down. So depending upon when I open up the potassium channels is when this thing starts to go back down. But suppose I open up potassium channels here. Open potassium channels at this point. So now what I'm going to see, now it's going to start tailing back down. Now if I keep both the channels open and it's a 50-50 distribution, I think you have an idea of what's going to happen, which is it's going to head back down and it will settle on minus 14 millivolts, you see. So you quickly can figure out that if you let me control the permeability of the membrane of these two electrolytes, sodium and potassium, then I can make that membrane potential dance. I can make it go up, I can make it go down by me just pulling levers, opening and closing channels. So now let's make it really, really complicated. Last scenario here. Let's say we open up sodium channels, okay? But then after a certain amount of time, we close them down. So we let them open and we close them. But before we close them, we're going to open up potassium channels. And we're going to let them stay open for a certain amount of time. So we're going to allow the potassium channels to be open longer than the sodium channels. And then after a certain amount of time, the potassium channels close. So we end up where we began in terms of the permeability of the membrane relative to these electrolytes. So let's play it out. Then what would happen? Okay, so we open up the sodium channels. So here we go. So we're starting at minus 70, and so we're zooming up. We're heading up, we're heading up, we're heading up. Okay, so now we're going to approaching the plus 60 millivolts. Now what's going to happen is that suppose I just let it be open till it reaches the near 60, and then about this amount of time, or about this time, then I open up those potassium channels. So now at this point, potassium channels open. So that, of course, is going to bring it back down to, again, approaching the minus 14 like we had on the prior one. Except as it's heading back down to minus 14, okay, we close those sodium channels. Sodium channels close. So sodium channels close somewhere in here. Sodium channels close somewhere along in here. So that means if the sodium channel is closed, then now the minus 14 is off the board. So there's nothing now impeding the potassium from dragging the membrane potential down to its Nernst value. So it's going to head south. It's going to go down, 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 until when? Until it reaches the minus 88 value. Minus 88, because that's the Nernst value here. So I'll just, let's just correct that a little bit here. Nope, didn't want to do that. That's what I want to do, and I didn't want to do that either, so hang on. So let's try that again. So I want to there, and we're going to go here. Boom, boom. Okay, now we're going to go red again, redraw that. So it's heading down, 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 down. Okay, now it's going to hit the Nernst value there. So now what happens at this point? Close potassium channels. So now as we close the potassium channels, now we return the membrane to be what it was originally, which means then that this membrane, this potential now is just going to start drifting up, and then we'll reestablish where it began already, its resting membrane potential. Now, why is it going up back to its minus 70 resting membrane potential? Because now I've returned the membrane to its normal state where, again, I have some leaky potassium, I have some leaky sodium and such. So it's returning to whatever the forces were that were establishing at minus 70 millivolts to begin with. So I return to normal resting membrane potential. But note, during this cycle here, from here to here, there is no resting membrane potential. It's dancing around because I am opening and closing potassium channels in sequence and, with all kind of, open here, close there kind of thing. And again, so if I'm controlling the channels, I can make this thing dance. So since you already have a pretty good idea of how an action potential works, you know what I've just shown you is an action potential, because this is roughly what happens during an action potential. Now, the mechanisms behind that is something that we will, of course, discuss later on, but this is basically it. So let's now go to a classic study by Hodgkin Huxley, where they did this in the 1950s when action potentials were pretty much a mystery. And so they were working on a giant squid axon, and they were recording, or they were trying to figure out how action potentials occur, and they were zeroing in on the activity of sodium and the activity of potassium. And they did groundbreaking work on this. In fact, they won this little prize called the Nobel for this. It was big stuff back in its day. So what we have here is several things going on. So first of all, let's take a look at our axes. Well, first of all, time. Now, note the time scale is in milliseconds. So things are happening pretty fast. Now, we have two y-axes, as a lot of these diagrams do, which means they're communicating two different things. So on screen left, we're measuring conductances. And remember, the conductance is going to be millimos per square centimeter because we're dealing with, again, a cell membrane. And so with the conductances, what we are measuring is the conductance of sodium and the conductance of potassium. So here is the conduction of the sodium, going up like that, and then it goes down. On this side over here, we're measuring the action potential. So that's going to be screen right. That's, again, millivolts. So we are measuring action potential over here. So there's my action potential. It's going up, it's going down, and then it's drifting back, and we'll eventually return to minus 70. So, and that's roughly what we saw in the prior page. So what they're trying to do is kind of connect the permeability and the current of sodium and potassium moving and how it relates to the action potential. So, but let's go ahead and look at go back to the sodium story first. So I got sodium here. Now, mind you, again, I have to be careful with this. We are looking at permeability. We're not looking at current directly. It's permeability. So what we want to be mindful of here is that we are seeing that we're having, through the action potential sequence, we're having a variable permeability. And this variable permeability for sodium, which means we're having a variable conductance because we're dealing with the charged particle here, is that we're opening and we're closing channels. So during the action potential, we see the conductance going up. We're making the membrane permeable, more permeable to sodium, and then it's going back down. So we're making the membrane less permeable to sodium. And what we see here is we have a permeability of sodium, and again, it's not zero, but it's close. So it's very, very low here, and it returns to very, very low. And note the time span that this happens. So we're talking from here to here. So it's less than a millisecond. So we have some channels that are opening and closing in less than a millisecond. They open and they close very rapidly. So when you have the opening, that means I'm having now movement of current. And why would I have movement of current? Because the resting membrane potential is very far from where the sodium is. Remember, the Nernst equation says we're going to call it sodium be plus 60. And so again, you'll recall our relationship here. We have conductance is going to be the quotient of current over voltage. Or we could say that the current or the amperage is going to be the conductance times the voltage. Okay, again, strong mathematical relationship here, Ohm's law. So as I increase the conductance, you see, that is going to be causing an increase in the current. So I'm going to have sodium coming in. And the fact of that, the current of sodium coming in, then in turn affects the voltage. So they're all related. So we see then the race upward towards the Nernst value for sodium, and here they have it at that. Okay, that's my Nernst value. So that's that. So it's going up. So we have another player, and that is potassium. So let's go potassium, we'll go purple. So I got potassium here, and so potassium, there we're mapping the conductance, and so it's going up, it's going down, and of course returns to baseline. Then again, the original conductance for potassium is not 0, but so the graph is a little funky on this point, but that's okay. Point being is that the potassium channels begin to open very soon after the sodium channels open. So maybe a little bit of a lag time, but potassium channels are opening almost the same time as the sodium, not quite, but almost. But you'll note that the peaking of the permeability for potassium is about here. So, and this is where we are in terms of permeability of the sodium. So as the membrane is returning to, very rapidly returning to being almost impermeable to sodium, I'm just at that point peaking with the permeability of the potassium. You'll also note the time span of the potassium channels being open is exceeding a millisecond. So the potassium channels, they open and then they close. So the permeability is changing. It becomes more permeable and less permeable. But the timing of the opening and closing of those channels are much slower than they are for sodium. So we have a timing dynamic here as well. So the opening and closing of the sodium channels very rapidly, open, close. The opening and closing of the potassium channels much more slow. But with the opening of the potassium channels, making it very permeable to potassium, that then allows for this membrane to go to near the Nernst value for potassium. And then note that as the potassium channels begin to close, this thing starts drifting back to normal, just like what we said earlier. So this is in a sense a rehash of what we said earlier regarding the movement of these electrolytes. I do again want to remind you, and so we'll just kind of go down here, of the relationship, and this is review. We can look at it graphically. Recall that we have, again, a G is going to be the change of current over the change of voltage. So in a sense, we could say this is, delta, delta and delta. And if we put it in graph form, we have our x-axis. That's going to be volts. Our y-axis, that's going to be my current. And then, again, if you graph this out as we did earlier in the membrane potential, again, you get a line. Okay, we'll make it roughly there. So that's a function. And of course, this is a function that can be graphed. So it's linear, as you understand math or understand algebra, that's a linear function. And it has a slope. And so what we have is a change. For every change in voltage, we're going to have a change in current. And so in this case, if G equals to 1, that means for every 1 volt, we have 1 amp change. So the G is the slope. So this is my G value. So G is slope of this line. Now, this relation here, G is static. I'm not changing G. But if I were to change G, depending upon how I change it, that determines then the change of the slope. And so maybe I am making the membrane to be more permeable to electrolyte. And if it's more permeable to electrolyte, that means I can change a volt and I'm going to get a bigger change in current because it's more permeable. So then I would increase the G, and so let's just call it maybe up to there. So maybe that's my new G value, and just call it, for kicks, just say G equals now 2. So now I've got a change in volt, and then I've got change in amperage. So in this case, roughing it out, for every 1 volt change, I'm having a 2 amp flow of current. So now I have a new slope, 2. Or I could go the other way. I could say, let's make the membrane to be less permeable to the electrolyte of interest. And so we could say, okay, well, let's just make it somewhere along in here. All right. And suppose here G equals to 1/2. So I've made the membrane to be less permeable to the electrolyte of interest. So I would say then that I'm going to have a voltage change and I'm going to have an amperage change. But now, let's just say for every 1 volt that I change the membrane, I only have a 1/2 amp current. So one of the points that I want to make sure you don't get caught on this is that when we're looking at changes in G value, that doesn't necessarily mean I'm going to have an increase in current. It depends. If I were to ask you, okay, I have a situation and I have made the membrane to be more permeable, I've increased the G value, and then I ask you, will that necessarily mean that I have an increase in current because I increase the G value? Your answer should be, it depends. Are you holding the voltage value the same? Well, if I'm holding the voltage value the same, then yes. I got this equation here. If voltage is not changing and I increase the G, then that means the amperage must also increase. But you have to qualify it. If all you know is that I've changed the G, but I haven't told you anything else, and I ask you, would an increase in G necessarily result in an increase in I, or amperage, the answer has to be, it depends. Are you or are you not maintaining the voltage? Because you can certainly see that I could increase the G, but also decrease the V, such that now the amperage remains unchanged. Perhaps maybe I took the G, just rewrite it here. Can you see? So what if I doubled the G, so 2 times increase of the G, but what if I cut voltage in half? Then what happens to the I? The I remains unchanged. So you see how this works? So just because you have an increase in the G doesn't necessarily mean I'm going to have an increase in the I. I have to pay attention to what happens in the voltage. So just be careful with that nuance, that this is a 3-variable equation, and you can work it multiple different ways. So just be careful with that one. Okay, so I hope this helps us understand the relation of conductance and the amperage relative to voltage. Again, just always bear in mind that this is a function and that I have a 3-variable equation here, and you can obviously manipulate in lots of different ways. So again, take-home point here is that action potential is caused by a very complicated interaction of voltage-sensitive channels of sodium and of potassium, and we're going to learn later how this works, that the sodium opens and closes very rapidly, and the potassium channels open slowly and remain open longer, but both of them will eventually close, allowing the membrane to return to its normal resting membrane potential. So anyway, so we'll bring this one to a close. I want to pick back up on what we call depolarization. The depolarization happens when you have a critical number of voltage-sensitive sodium channels and they're opened up at the same time. So what I don't want you to walk away with thinking that if I open up one sodium channel, that the sodium coming in to that membrane is enough to set off an action potential. It is not. You have to bring the membrane to threshold, and we got a diagram on the next page that shows this. So if a resting membrane potential, say, is at minus 70 millivolts, there is a depolarizing event where I have to bring that membrane to something less negative to minus 70, if minus 70 is a resting membrane potential, such that then it affects an action potential. So the start of an action potential is when I have enough voltage-sensitive sodium channels open at the same time, allowing enough sodium to flow in, enough positive current to flow in, that it in turn trips off other voltage-sensitive sodium channels to start the chain reaction. But I have to have enough for that to occur. So when a stimulus is larger than the threshold, the size and the shape of the action potential doesn't change. You either have an action potential or you don't. Or in science parlance, action potentials are all or none. So let me illustrate the following way. Suppose that I have a membrane here. Okay, so there's my membrane there. And this is going to be out, and this is going to be in. And now just for kicks, let's just assume I'm going to ignore the potassium and say we have now an array of voltage-sensitive sodium channels. Okay, voltage-sensitive, voltage-sensitive, voltage-sensitive. Boom, boom, boom. And let's suppose that in the resting membrane potential, let's call it minus 70 millivolts. So now I want to depolarize the membrane. I want to bring it to threshold. So let's just say I'm going to do so by using a battery. So if I have a battery here, and again, I'm going to go silly numbers on you. Let's just say that the membrane has to be raised to at least minus 65 millivolts before I have an action potential. So I'm going to have a battery here, and I'm going to raise it to minus 65 millivolts. And if I do it quickly enough, quickly raising it to minus 65 millivolts will then get me enough voltage-sensitive channels that are open at the same time. Remember, these things open and close rapidly. But they're going to be enough open at the same time such that it now causes the downstream voltage-sensitive channels to open. So now I'm having an action potential that's going to progress down this excitable membrane. But I had to have enough stimulus to get the thing going to begin with. So if I have enough energy put into the system from my battery to effect an action potential, then I would say that I have brought the membrane to threshold. Once you bring the membrane to threshold, You either have one or you don't, and in this case, you would. So putting additional energy in, suppose I quickly made it rise not to minus 65, but maybe it's minus 60. Okay, really put an extra bit of oomph in the battery, bring it to threshold. I'm still going to have the same action potential downstream. So adding energy to the system is not going to give me a bigger action potential. I just have to have enough to bring it to threshold. And if I can bring it to threshold, that's all I need. So the analogy that I like to use with this is, and we've probably all done this as kids, dominoes. So you set up a series of dominoes, and then you tap the first one, and then you get the chain reaction. And you can all go to YouTube and see these elaborate domino rooms where somebody has spent, a month setting up this massive room of dominoes, and then they hit the first domino, and of course it has a beautiful display that we all enjoy, and it's pleasing to the eye. I don't know who these people are that have a month to do that, but that's their deal. So here's where the analogy comes in and it's useful. Suppose I have a long row of dominoes, and you put some energy into that first domino, and it rocks back and forth, but then rights itself. But it wasn't enough to cause the reaction. And then you tap the domino a little harder, and it rocks a little more, but then it rights itself and no reaction. So then you up the energy. You hit it a little harder. Now you've tipped it to where now it's going to tumble and hit the next domino, and then that one's going to hit one, and that one's going to hit one. So now you then have the chain reaction. So putting enough energy in that first domino to where it will actually tip and cause a chain reaction, we would say then you've reached threshold of the domino. But note the following. You now know how hard you have to hit the domino to get the chain reaction. What if you hit it even harder? Maybe you doubled the thump of the first domino, so you smack it really good. So if your domino chain is very long, say 20 feet, well, 10 feet away from your first domino thump, is it going to make a difference? The answer is no. Whether you put enough energy in that first domino to start the reaction, or whether you put a lot of energy in that first domino to start the reaction, the downstream effect is the same. They tumble the way they tumble. So that's a nice way of looking at this all or none thing regarding action potentials. All you need to do is bring it to threshold. Going beyond gets you nothing. You're still going to have the same action potential profile. Now we also have repolarization. So we'll go a different color here. So now we have in this diagram a bunch of, go back to green, is what I wanted to go. So now I'm having green being the potassium channels. Potassium channels would be the green, they're voltage sensitive, so voltage sensitive potassium channels. Remember from this diagram up here, the potassium channels are the ones that bring it back down to regular resting membrane potential after they open and then they close. So you have the potassium channels. They're also voltage sensitive. They will open and they will close, and we'll see how they do it differently than the sodium channels a little bit later. So these voltage sensitive channels, they're going to begin to open as the membrane rises above. This one says minus 90, but it depends. I think one up here we're talking about rises above minus 70, but it doesn't make any difference. It varies. Point being is that they begin to open up, and that is going to be the energy. You're going to have potassium effluxing, which is a fancy way of saying it's going to be potassium is going to be leaving, and if potassium is leaving, now they're carrying positive charge out of the cell, which makes the inside of the cell more negative, which is why it's being brought down to its original resting membrane potential. You have a lovely chemical called tetraethylammonium, TEA, and it selectively blocks voltage-sensitive sodium channels, which is kind of interesting. And we've got a diagram on the next page where we're going to talk about that because, it's very common in neuroscience. And it allows you to see what happens in an excitable membrane. What would happen if you poison those voltage-sensitive potassium channels? What would the action potential look like? And we're going to find that out in a second. So again, depolarization, repolarization. So let's go to our next diagram we have here, and let me go ahead and I'll get this cleaned up for you. And we will take another look at it. Okay. So what we have here is we have again, showing the action potential. We got a minus 70 millivolts. Okay. So this is going to be our stimulating current. So this is our battery. Battery here. So what we have here, again, this is the energy. So this is time. This is in milliseconds. So 1 millisecond, 2 millisecond. So I'm turning my battery on. And let's just say for kicks that I turn the battery, I'll go different colors. I'll turn the battery on, and I'll go blue here, and I'm raising it to that level. So I'm now putting energy into the system. Doing so, I raise the membrane potential from minus 70 to something a little less negative, and right there, and then I turn the battery off. So when I turn the battery off, it goes right back down, and you'll note that I didn't have an action potential. I put energy into the system, but it wasn't enough to bring it to threshold. So the membrane potential went up and it went down. It went less negative and then back to its resting membrane potential. We have a term for that. We call that a graded potential. Now let's make sure we understand what a graded potential is. The best way to think of graded potentials is a light dimmer. Or physics, it would be a rheostat. So as you turn the light knob, it gets a little brighter, a little brighter, a little brighter. You turn it down, it gets a little darker, a little darker, a little darker. So you can grade it. It's gradations. So as I put energy in the system from the battery, I raise it here. I'm going to have a graded potential. It's going to go up and it's going to go down. Light dimmer. I did not have an action potential. So that would be a graded potential. So a graded potential is where I do something to change the membrane potential in a graded way, and an action potential does not follow. Okay? So a graded potential can lead to an action potential if I depolarize, or it may not, depending upon whether the graded potential was enough to meet threshold. So my little blue scenario, it wasn't. So let's turn the energy up a little bit, and we'll go green. So now I take the battery, and so now I'm going to even put more energy into it. So now I see up here in green, I'm having a graded potential, but I don't have an action potential. So when I turn the battery off, it goes right back to normal. So I had yet another graded potential without an action potential. Obviously, that was not enough energy to effect an action potential. So now I'm going to turn the battery up even higher. So we're going to say, let's go, we'll bring it to here. That's higher energy. And so here we go, graded potential up, and then all of a sudden, bang, I now have an action potential. So I put enough energy into the system, having a graded potential that reached the threshold, which meant I had enough voltage-sensitive sodium channels opened up at the same time to start the chain reaction. And so then I have my action potential. But again, you either have one or you don't. Now, I could have, I'm going to add the thing here. What if I said, okay, I'm going to really juice it. I'm going to go up here and make it even more energy. Then what would happen is it would go up here, okay, reach threshold, but I would still have the same action potential. Now, as you're working through the action potential, you have what we call depolarization, which I've never really liked that term. Because I think to depolarize meaning bringing it to neutral. Because if it's sitting at minus 70 millivolts, that's pretty polarized. So, but as it zooms up to the top of being near plus 60 millivolts, that's still pretty polarized. So the only time it's not polarized is when it's at its zero voltage. That means no potential across the two. But, it is what it is. We call it depolarization because as it goes from minus 70 to 0, it is, in fact, depolarizing. But as it shoots back up to plus 60, we still call that depolarizing, even though it's not quite. So we kind of have to live with a little bit of ambiguity in terms. So in parlance, really what we say here is that this first phase here is my depolarization, even though I'm going well above 0 here. And then the repolarization is basically another way of saying it's returning to normal resting membrane potential. So the depolarization, or repolarization, is the downswing. But you'll recall, because the voltage-sensitive potassium channels are open up longer, that it goes actually more negative relative to resting membrane potential. So what we would say here is that we are now hyperpolarizing the membrane. It's more polarized than normal because temporarily it's sitting at the Nernst value of potassium, but then it drifts back up to normal resting membrane potential. So that's how we employ the vocabulary. So the hyperpolarizing phase of it, again, these voltage-sensitive sodium channels are slow to close, as we saw earlier, in making it near the Nernst value, but eventually they close and it drifts back up to normal resting membrane potential. So let's close by considering TEA. And remember what TEA does. It poisons or it inhibits those voltage-sensitive potassium channels doing what they do. So this is pretty simple. How would, if you had a giant squid axon and you were bathing it with TEA, how would that alter the action potentials if you could get one going? Well, if you did that, you would put a stimulus, you would bring it to threshold. So it's sitting at minus 70 millivolts. You stimulate it, you bring it to threshold, so now you're going to have enough voltage-sensitive sodium channels to effect an action potential. So it's going to shoot right up there, boom. Okay, but is it going to stay up there? And the answer is no. Why? Because the voltage-sensitive channels, they open quickly and they close quickly. So the membrane becomes temporarily very permeable to sodium, but then it quickly becomes very impermeable to sodium. But I'm not having my voltage-sensitive potassium channels opening up. So I've lost one of my factors that drags it back down to repolarize. So the question is, will it now repolarize, or will it just hang up there at plus 60? Well, the answer is it is going to still repolarize. It will repolarize without the voltage-sensitive potassium channels. So why would it repolarize? It would repolarize because even though the voltage-sensitive channels have been stopped, complements of TEA, I still have all the leak channels at play that normally keeps the resting membrane potential at steady state at minus 70. So what would happen? would be that this membrane potential would drift back down to resting membrane potential. But the only forces bringing it back down is just simply going to be your garden variety leak channels that are present regardless. So it would go back down to resting membrane potential, but what would not happen is you would not have any hyperpolarization, because the hyperpolarization was because of those voltage-sensitive potassium channels. So it would shoot up like a regular action potential and then just gradually drift back down to resting membrane potential, and that's what would happen. So that's how TEA would affect an action potential. Okay, hope you find this helpful. See you next time. I would like to go back to our Nernst equation, and the Ohm's law. And so we have a relation here, of course, Ohm's law. Voltage is a product of current and resistance, or I could say voltage is a quotient of voltage over resistance. But I could also talk about it in terms of G, and we've had this expressed before various ways. G, of course, is 1 over the resistance. I could write the equation this way here, that the amperage, the actual flow of charge, is a product of G and V. Remember, we had been saying G is going to be equaling the current over the voltage. So this is just another form of that, of course. But we want to put it in terms of I. In other words, amperage is equaling something, to get a sense of what the amperage actually is and relate it to the action potential itself. What we can do is we can take this V value here, or the V value here, and we can substitute that voltage to the difference between the resting membrane potential, be the resting membrane potential, or I could also say the potential, the membrane potential at any point in time. Okay, so it'd be resting membrane potential or the membrane potential at any point in time, because when we see an action potential, it's changing, of course, so we can freeze frame it and say, okay, what's the potential at that point? So any point in time. Then what I want to do is I want to compare that to this, and this is the Nernst value for the electrolyte, whatever it is, sodium, potassium, pick your favorite. Because you'll recall that the flow of current, when you look at that equation, at a given voltage, the flow of current is going to be a function of how far the membrane potential is from the Nernst value for that electrolyte. So if I'm wanting to know what is sodium doing, what's the amperage of sodium, what's the flow of sodium, I would look at the membrane potential at a point in time, and I would compare that to what the Nernst value is for, in this case, sodium. And what the difference is will drive how much current I have. So obviously, in a common sense way, the farther the membrane potential is from the Nernst value, and assuming that I can have some degree of permeability for that electrolyte, then the farther away it is from the Nernst value, the membrane potential, the greater the amperage. So I can rewrite the equation in this form here. That the flow of the ion, the current of the ion, I ion, is equal to whatever the G is times the membrane potential at a given time minus the Nernst value for that ion. So I have to look at these at one at a time. So I would look at potassium, I look at sodium, I look at chloride to estimate what the flow would be in a given situation. So this here, of course, is delta. It's the difference between the two. So you would note that if the membrane, just looking at this equation here, if the membrane is at its Nernst value, then the delta here is 0. So if I have no potential difference relative to that particular Nernst value, then I is 0. I get no flow. And why do I get no flow? Go back to what we talked about earlier in terms of vector forces on an electrolyte. If the cell membrane is at its Nernst value, I have no net force acting on that electrolyte. I have an electrical force acting on it. I have a concentration force acting on it. But if the membrane is at Nernst value, those forces are of equal magnitude but opposite directions. So when you add the vectors, the net vector is 0. Therefore, if no force is acting on that electrolyte, I'm going to get no net movement of charge. Whereas you can clearly see, the greater the delta, if it's very far away, I'm going to get a larger I just by the way the equation works. So again, an example of what I've just said is that if the membrane potential, say it's sitting at minus 90, and the Nernst value for potassium is minus 90, then the actual flow is 0 regardless of conductance value. Now, again, fine shading it here. If I'm getting no flow, then there is no G value. Remember we talked a bit about this earlier. If I have no flow, then there is no Ohm's law in the sense of there's nothing to work with. So if I equals 0, then G is meaningless. Okay, you just go back to Ohm's law, V equals IR. If there is no I, then there's no mathematical relation. If there is no I, there is no V. And again, mathematically the equation falls apart. So if you don't have a flow, then there's no point in looking at the Nernst value or looking at the Ohm's law, because again it dissolves to being indeterminate, nothing. So again, if I have no difference here, then that means no flow, and if no flow, then there's no mathematical relationship in the sense of at that point in time when there is no flow, then the G is meaningless. And again, back to my earlier point, it's sort of like holding the naked wire up, declaring that this wire has a resistance. What you're really meaning is that if I have voltage and potential, and flow, then I could come up with a resistance of the wire. So, but if there is no flow, then really there is no resistance. So resistance and conductance is only couched in terms of if there is flow of charge and if there is voltage, then I have a G value. Okay? All right, so plugging in here, you get minus 90 minus 90. That equals to 0, therefore no amperage, and that's it. Now, one subtle thing here that you want to be sensitive to when you're working with Ohm's law, and that is if you're given units in millivolts or milliamps or picoamps or whatever amperage, whatever units we're talking about, millimos, that if you're going to plug into the Ohm's law equation, you must convert all of the units to ohms or to mhos or to volts or to amperage. You have to convert back to base units before you do your arithmetic. Work the arithmetic, and then if you want the final answer in milli, then after you've worked the arithmetic, then convert it back. If you multiply millivolts in milliamps, you're going to get the incorrect answer because the decimal place will not be in the correct spot. This is why we're converting these to voltage first to run the calculation. So this next paragraph, I've kind of made this point to you before, is that you have to be careful when you are thinking in terms of G values to remember that conductance alone does not indicate a change in amperage. You have to know what the voltage is first. So I'm just hitting on that point one more time. And that the closer the membrane potential is to the Nernst value, which again also known as a reversal, the less amperage will be at a given G value. So a greater G does not necessarily mean greater amperage. That depends on the volts. And again, I made that point before. So again, returning to this diagram here, you see that I have a variable G for sodium, and I have a variable G for potassium. So I have a lot of things happening at the same time as I am working through this formula here. Let me clean that up. Where am I? Okay, this formula here. I am having a G that is moving the whole time. I am having an EM is moving the whole time. Now, my Nernst value stays the same. But if this is moving and this is moving, then this is going to be changing. So it's very dynamic as you work through the action potential. So this formulation here is very powerful in terms of understanding if you freeze frame during an action potential and say, stop, what is the flow, what is the amperage at that given point in time, you can make that calculation. So I could look at this diagram here and estimate what the amperage would be. If I know a G value for sodium, and I know the potential at that point in time. So there's my time there. So at that point, I can look at the potential, I can look at the G, and then I can estimate the amperage. So that gives me enough information because I also know what the Nernst value is for the sodium. So you can estimate the amperage from those data there. Okay, so we will close this one at this point and pick up next time. I want to introduce you to a concept called the length constant, and it is also known as the space constant, but I'll probably refer to it as the link constant. So what I'm going to do is toss out the verbal salad for the definition, which you probably won't understand. But here it is. The link constant is the distance over which the potential change decreases to 37% of its maximum value. Okay, while that is the definition, it can be a little opaque, so my job now is to unpack that for you. And I will do so by doing some examples. The maximum value is the difference between the highest and the lowest point of potential recordings. The link constant is always in terms of length, so it is in terms of millimeters. In a typical link constant for a mammalian axon is typically 1 to 3 millimeters, whether it be nerve or whether it be muscle. Okay, so let's consider the following. And I'm going to make a pass at it now, but I'm going to come back later and have a more detailed, a more full discussion of link constant. But I did just want to soften you up with the concept to begin with. So imagine that I have a cell membrane. Now this cartoon here has it as a neuron. But I'm going to indulge you, or I'm going to ask you to indulge me and just assume that this axon here is non-excitable. Let's just pretend that you can't have an action potential. So now all we're dealing with is just the various other non-excitable, non-voltage sensitive channels at play here. Okay, just say the leak channels. So if you will, just ignore that it is an axon and just pretend it is a non-excitable membrane. Okay, so assume no voltage gated channels. Okay, we're just making that assumption. Okay, only thing I got going on is leak channels. So imagine if I had a little battery. Okay, put a battery there, and let's just say for argument's sake that the resting membrane potential is minus 70 millivolts. So the whole membrane is minus 70 millivolts. And suppose that I have a battery and I dial it up and I make the membrane at this point here, because of the battery, I turn it and I make it to be plus 50 millivolts. The battery is doing it. The question is, what would the potential be here? Now, mind you, axons, again, we're assuming no voltage sensitive channels here. I'll remind you that there are some action potentials in your central nervous system that are 2 and 3 feet in length. You got neurons, motor neurons that live in your motor cortices in your brain, and they go all the way down to the lumbar section of your cord, rather impressively long. So imagine this axon is 3 feet long. So if I take a little mini battery and I make this little region here to be plus 50 millivolts, the question is, will the end of the axon 3 feet away, will it be 50 millivolts positive? And of course the answer is obviously not. The membrane potential 3 feet away is still going to be minus 70 millivolts. So it will be unchanged. So what happened from here to 3 feet away? Well, what happened is leaking happened. Because as I take this membrane here and I hold it at plus 50 millivolts, I'm not just bringing it up to plus 50 millivolts and letting it die down. I am keeping it. I'm holding it at plus 50 millivolts because of the battery here. You will understand that the farther away I get from the battery source, the closer and closer the membrane potential will be to resting. So maybe here I'm at 45, and then maybe here I'm at 40, and then maybe here I'm at 30, and then on and on and on until at some point I'd be minus 70 millivolts and is unaffected. Well, why the fall off? Well, it's not falling off here because I'm making the battery hold it there. But the farther away you go, what I'm doing is if that membrane is sitting at plus 50 millivolts, that means I've moved that membrane very far away from the Nernst value for potassium, which means potassium is going to be flowing out. But if it's flowing out at the point of the battery, it doesn't do any good because the battery is maintaining that plus 50 millivolts. But as I get farther away, I'm having potassium flow out, and the potassium is more effectively bringing the membrane potential down to closer to resting membrane potential because I'm getting away from the electrical field of the battery. And you'll recall that if I have an electrical field, the farther away from it, the less potent it is. So as I distance myself to the battery, a little itty bitty little old battery, then the battery is losing its effect, and then I'm able to have the flow or the egress of potassium out of the cell, bringing it back down to normal. So I have a decreasing pattern here the farther away I go from the battery. So the pattern of decrease, what's the pattern that it becomes less and less? That depends upon the nature of the cell. It depends upon the nature of the leak channels. It depends on whether the cell is insulated or not. So a lot of factors go in determining what the drop-off is once you get away from the battery. So the concept of a length constant is a way of quantifying the nature of the membrane relative to drop-off when you have a depolarizing event, so in this case, the battery. So let me bring it home to exactly talking about the percentages and such. So we would say that if I have a battery and it's sitting at plus 50 millivolts, and I say that length constant of this cell membrane here, length constant of cell membrane here, the one I'm looking at here, I'm saying length constant of cell membrane is equal to 1 millimeter. I'm just saying, suppose the length constant of this cell membrane was 1 millimeter. So what am I saying? So assume that the distance from here to here is 1 millimeter. So I'm curious then of what is going on at that point 1 millimeter away from the source of the battery or the electric field. So the question is, what is the membrane potential 1 millimeter away from the battery? And we have our answer here. I can calculate it. If I know the resting membrane potential, if I know what the battery is holding it as, and I apply the 37%, I can calculate or I can estimate what the membrane potential will be 1 millimeter away from the battery. So let's do it and see what happens. So the first thing I want to do is note that the battery is causing a swing or a change of potential across the membrane from minus 70 to plus 50. So let's sketch it out. So I got plus 50. I've got minus 70. Okay, so I'm going from here to here. So that distance represents 120 millivolts. So that's the range. And so what the definition says, the distance, in this case the distance is 1 millimeter, over which the potential change decreases to 37% of maximum value. So what is the maximum value? The maximum value is 120. That's the range. And you recall from your high school math when you did word problems, when you saw the word of means multiply. So it would be 37% of maximum value. So that would mean that I would go 37%, 0.37 times 120 gives me 44 millivolts. So 37% of 120 is 44 millivolts. So that would be then the range we're talking about, 44 millivolts. I would take that 44 millivolts, which represents 37% of the total swing, and I would add that back to the resting membrane potential. So that means I would take minus 70 and I'd add back 44 millivolts. And whatever that value is, that would be the potential there. And so if you do the arithmetic, so it's minus 76 plus 44, that should give me minus 26 millivolts. So therefore, the answer to that question is 1 millimeter away from the battery source. The potential would be predicted at minus 26 millivolts. Now let me address a side point here, which is why 37%? Why not 50%, 75%, 99%? So why 37%? There is a lot of electrical theory behind this, but I'll just get to the point. In physics, in electrical type of calculations, the value of E, you'll recall that you have certain constants in nature, and E is one of those constants. You got pi and other such. Well, E is 1. Well, it turns out that the inverse of E equals 0.37. So that is where I get the 37%. It's based on the inverse of the E value. Okay, so I've run through this calculation, but let me loop through one more time to make sure you're understanding what I'm saying. The length constant of this membrane is 1 millimeter. Let me tell you what the length constant is not of this membrane. It would be incorrect to say that the length constant of this membrane is minus 26 millivolts. That's not true. The length constant is a distance. So let me do just a quick hypothetical. I'm not going to run through the math, but you can do this. When you go into a situation and I tell you, okay, the length constant is 1 millimeter, then you can calculate the potential 1 millimeter away regardless of what the battery is. If you did this problem again and said, okay, instead of the battery being plus 50, I'm going to make the battery be plus 25. All you would do then is run the same calculation here except plus 25 as opposed to plus 50. Do the same math and you will get a new potential at this point here. It won't be minus 26, it'll be something less. but it will still be a 1 millimeter length constant, you see. So I guess a question that could be raised would be, how does one calculate a length constant? Because on this example here, I told you on the front end, the length constant is 1 millimeter. Suppose I were to present you a cell membrane and you had the appropriate equipment to do so, and I say, okay, calculate the length constant for me. What you would do in a theoretical way, you would take a little battery, you would put it at plus 50, shall we say? Now, you don't know the distance. You don't know it's 1 millimeter. But what you would do is you would go through these exact calculations. You would come up with minus 26 millivolts, and then you would take a probe and measure here, 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 and then you would see how far out you got before you hit minus 26 millivolts. And when you found that distance, then you have calculated your length constant of being 1 millimeter. So you'll note none of these calculations here had anything to do with the distance. All you're after is coming up with a number. And then once you know what the number is, you then go to the cell membrane and find out how far away from the battery do you have to probe and measure until you get whatever that calculation is, in this case, 26. You could then change your, if you're accurate, you can then change the battery to say 25, come up with the whatever the new value is, and then if you've done your arithmetic correctly, and you have a preliminary notion that the length constant is 1 millimeter, then you should be able to get that distance, and it should be spot on whatever that new value is when you change the value of the battery. So that's kind of how that works. Okay. All right, we're going to come back to length constant later because it's very important in physiology that you understand that, and we're going to apply it in different context. Okay, so here is just a repeat of the graded potential, threshold, such. Okay, I've restated this here. That again, threshold is when you have a depolarization event that requires enough of these voltage-sensitive sodium channels to open up to effect an action potential. So it's just kind of a bit of a repeat, but we'll make sure you get that point. Let's turn our attention to the channels themselves and then also the concept of absolute refractory period. And these two are related to each other. An absolute refractory period is that period following an action potential where another action potential cannot be initiated because these sodium channels, these voltage-sensitive sodium channels, will not open. So let's take a look at the nature of the voltage-sensitive sodium channels and the nature of the voltage-sensitive potassium channels. And they're really quite different. So let's do a thought experiment. This is actually a real experiment. We're just going to think about it. Imagine you have a way of measuring conductance, and again, millimos per square centimeter. And the resting membrane potential is minus 90 millivolts. That's where it lives. So what we're going to do is we're going to use our trusty old battery to change the membrane potential to plus 10 millivolts. So, okay, this is going to be from a battery. So I'm going to turn that dial, and I'm going to keep it at 10 millivolts. So note I have time here, okay? So that means from this time to this time, by virtue of my battery, I am maintaining plus 10 millivolts. And then at the end of the 2 milliseconds, I turn the battery off, and I quickly go back to minus 90 millivolts. So what we're wanting to do is we're wanting to measure the change in conductance. And we're measuring how does the potential across the membrane affect the permeability of that membrane relative to either sodium or to potassium. Well, when I turn the battery on to plus 10 millivolts, what I find out, if I'm looking at my sodium, that I have a very quick increase in the permeability or the conductance to sodium, and then I discover a very rapid decrease. And despite the fact that I have held that membrane to plus 10 millivolts, I have a swing up and a swing down relative to the conductance. Now again, with this setup here, I need to emphasize this, I am not talking about an action potential. I'm just looking at the change in conductance, the permeability. So I'm not causing an action potential to occur. So that is not an action potential. Well, let me mess that up. Okay, not an action potential. I am measuring change in permeability because of the battery that I'm holding steady at 10 millivolts. So I find out something very different. So when I discovered, or when I look at the sodium response, the membrane relative to sodium permeability, it's very permeable and then it's quickly not permeable, even though I'm still at 10 millivolts. But when I look at the potassium, I turn it on at 0. I have the membrane becoming very permeable to potassium, even more so than normal. But what I find is that as long as that membrane potential is sitting at plus 10, the potassium conductance is consistent. It becomes very permeable. I'm opening up these voltage-sensitive potassium channels, and they remain open as long as the membrane is at 10 millivolts. But as soon as I turn my battery off, it quickly goes back down to normal. So that's very different than what you saw with the voltage-sensitive sodium channels. So why is that? Well, let's go with the simple one first. This over here to screen left are simply cartoons. Okay, so don't get carried away with the cartoon stuff here. The way these things are drawn are about as related to the real voltage-sensitive channels as a Saturday morning Fred Flintstone cartoon is to a real person. Okay, so they're just exaggerated cartoons, but it gets the concept across. So consider my voltage-sensitive potassium channels. What we have here is a single gated channel. So when the channel, or when the channel is in the context of a typical resting membrane potential, call it minus 90, then if the membrane potential is some less negative figure, and again it's a heterogeneous group, but when it is less negative, these channels begin to open. That channel opens here, allowing sodium to egress. So you have the range here because again it's a heterogeneous group in terms of what the set point is for that potassium channel. But as long as the membrane is at some potential, I don't know, call it minus 40 millivolts, okay, something like that, then that channel stays open. This channel only swings closed, or that gate swings closed, only when the resting membrane potential goes back down to below its trip point. So this is exactly what we see over here. As long as it's plus 10 millivolts, that channel gate is open, allowing potassium to leave. But as soon as you turn the battery off, this channel closes up. So it's a one-gated channel. Now let's look at the more complicated situation where we have the voltage-gated sodium channel. It turns out it's double-gated. So we have an activation gate, and that is also known in science literature as the M gate. And we have a inactivation gate, and in science that is known as the H gate. So I have an activation gate, inactivation gate, H gate, M gate. You'll need to know both. So when the membrane is sitting at its resting membrane potential, whatever that is, minus 90, minus 70, whatever it is, the M gate, or the activation gate, is closed, but the inactivation gate is open. As long as one gate is closed, then there's no sodium coming in. Now, when the set point for that particular voltage-sensitive sodium channel is reached, it will cause that activation gate, the M gate, to open. And when it opens, of course, sodium rushes in for a brief period of time. But what will happen for a whole host of physical reasons is that this inactivation gate, our H gate, and there's my H gate right there, my H gate is going to then close up. And so I now have this situation. So the H gate closes at this point over here in the graph, where that H gate closes, and then you have a rapid decrease in the conductance or permeability of the membrane to sodium because the H gate closed. So now sodium can no longer get into the cell. So I hope you can appreciate the timing between the M gate opening up and the H gate closing. So we got, what, 1 millisecond? So that means that the H gate begins to close in less than a half a millisecond from when it opened, or when the M gate opened. So it's a very rapid event. And so, of course, when the H gate is closed, doesn't matter if it's still sitting at plus 10 millivolts, the H gate is going to sit there and close. Now, to finish out the cartoon, what will happen as the membrane returns to baseline, or resting membrane potential, at some point, I'll just draw it here, the M gate will close while the H gate is still closed. So there's a brief period of time where they're both closed. And then after that, the H gate will swing back open, and now we're back to where we began. But in order for this to happen and then to return to resting point, or the beginning point, this gate here has to have the membrane to be near resting membrane potential. So as long as this is sitting at plus 10, it will freeze in that position there. And that gate is completely out of business. That voltage channel is out of business. It has to see the polarity of the membrane drop to near normal before it will reconfigure itself and turn back into the beginning. So this will be the basis of the absolute refractory period as you go through the action potential cycle, where if your voltage-sensitive sodium channels are in this state there is no way to have another action potential, because those voltage-sensitive channels, in a way, are not open for business. They're only open for business when they return back to this state here. So the take-home, the voltage-sensitive potassium channel is single-gated. It's simple. The voltage-sensitive sodium channel is double-gated with an activation, inactivation, or an M gate and an H gate. So no doubt, the notion of having to remember which is the M and which is the H is just one more thing to try to remember, and you do need to remember it, but I'm going to save you some aggravation so that you will never forget which is the inactivation gate and which is the activation gate relative to M and H. So here we go. I'm going to write a little phrase for you. Hi, Ma. That's all you got to remember. Hi, Ma. H, inactivation. M, activation. So when you get in a pinch and you're stressed on an exam, you don't know which is which, they refer to the M gate or the H gate, which is inactive, which is active. Just chill and say, hi, Ma, and you got it. So it's very easy to do. Okay, so I think this is a good place to stop. See you next time. We want to take another look at an action potential, but we want to do some comparisons for how the conductance of sodium and potassium are related to the action potential proper. So for this particular diagram here, we have our action potential is being mapped out here, and the action potential is, of course, a change in the voltage potential. So for that, we're using this axis here, membrane potential in millivolts. And so you see, minus 80 something up to near plus 60 something. And so that's the classic form of an action potential. What we're wanting to do is we're wanting to correlate that with the change in the permeability or the conductance. So we have our conductance being millimoles per square centimeter, of course, and we're focusing in on sodium and for potassium. So this is in line, temporal-wise, with the change in the sodium and the potassium conductances as it relates to the action potential up here. Now, you'll recall as we're changing the G value, changing the conductance, what we're doing by that is we're changing the permeability of the membrane relative to each of those electrolytes, because as you know, we have voltage-sensitive channels opening and voltage-sensitive channels closing. So it's correlating the change in the conductance relative to the actual action potential. And as you'll recall, that the G conductance is going to be a slope. And so we have we're basically graphing our voltage relative to our amperage or flow. And so what we have here is just simply amperage over volts. And of course, that's just simply slope y over x. And so we can have, again, a particular G value. Now, this diagram here, the G value is static. In other words, it's not changing. So you give me a G, and then I can plot because the G is the function, and you give me a voltage, and then I will give you a amperage. But the thing we'll be aware of here is that because the G value is so dynamic, that means that this function here is also changing. So I have an ever-changing slope of that function. But again, G value is dynamic, it's changing, which means I'm having variable permeability of the membranes throughout the action potential event. And that's basically all this is showing us. You also want to be impressed that for potassium, our baseline conductance is something just a little below 1 you see here. Okay, and then it's going to go from here to here. So maybe it's a little more than 10 times increase. So that's pretty impressive. But the thing that's really impressive is that for sodium, we're starting here at 0.005 conductance, and we're going all the way up to not quite 100, but pretty close to it. So you see that that is a many, many, many times increase in the conductance of sodium over its baseline, far more than the increase you see in the potassium. So it's very, very impressive. And as we said last time, the timing of the variability of the sodium permeability or the conductance is relatively short, and for potassium it's much longer because those channels are more slow. And then this final thing here is simply mapping out the ratio of conductance for potassium and for sodium. And so you'll note that when the ratio is 1, which is right there, then what that means then is that the conductances are the same. And here, again, they're the same. And so that doesn't surprise you in terms of the conductance ratio. And again, just because the conductances are the same doesn't necessarily mean that the amperage is the same. Again, you just need to make sure you understand that this is a complex relationship here. So again, much information here to think about, but again, don't oversimplify in the sense of, as I've said before, that G and I, while related to each other, are not necessarily the same, because you always have to consider the variable of the potential voltage itself. Okay? And again, just to remind you that when we're dealing with these types of equations, that when we're talking about a particular ion, that this is delta E. In other words, it's going to be the Nernst value. This is the Nernst value over here, and this is going to be the potential at that moment in time. But as you will clearly see during an action potential, that the potential is also very dynamic. So you have to kind of have to freeze frame and say, okay, if we freeze the action potential at this point in time, this would be the conductance, this would be the amperage. But since the voltage is changing, then of course the amperage is changing, but I'm also having the G value change. So basically what you have is you have this equation here. While the equation holds, I've got 3 things changing at once. So it's a pretty dynamic type of situation. Okay, so again, a very useful diagram. Here's just some verbiage. I'll hit the highlights on this. It's just a repeat of what we've already spoken of before in terms of M channels and H channels. And we're going to remember, hi Ma, there you go. So my M is going to be my activation, and my H channel is going to be my inactivation gates. So again, I think there's nothing new here, that when we have a depolarizing event, you're going to have that change in polarity, or that change in voltage potential changing the shape of the channel itself, and you're going to have an opening of the activation gate. Okay, so this is called the activation state, and that's going to be, again, when your M channel is open. So open M channel. And again, sodium is pouring through, of course. And then you're quickly going to have the inactivation gate. It's going to close, and again, that's going to be my H gate closes. And so when that closes, then that stops the flow of the sodium coming in. And again, we said at some point the inactivation gate is going to remain closed until it will not reopen until the membrane returns to near the original resting membrane potential here. So, and then when that's open, and of course the M gate is closed, then you're ready for another cycle. So I just ask you to refer back to the original cartoon on that, but this is kind of fleshing out what actually happens. We also know that the H gate is very important for the refractory period, and so this is what we want to look at now. We have an absolute refractory period and we have a relative refractory period. The absolute refractory period means there's absolutely no way you're going to affect another action potential. So a little cartoon here that shows that. Again, I have my action potential here, and my absolute refractory period is in the dark there, and that simply is meaning that the inactivation gate, the H gate, is closed. So H gate closed. And if that H gate is closed, which it is, then there's no type of event that can cause that H gate to open back up other than returning the channel or the voltage sensitive channel back to near resting membrane potential. So this would be the absolute refractory period. We also then have a relative refractory period. The relative refractory period is when you could have an action potential happening during that phase of the previous action potential, but that you're going to need more energy to do that. You actually have two periods of a relative refractory period, so I'm going to highlight that piece right there. That's easy to explain in the sense of this is hyperpolarization, of course. Hyperpolarization, this is where we have those voltage-sensitive potassium channels. Remember, they're opening, dragging the potential to the Nernst value for potassium. Remember, these are voltage-sensitive channels, so they're going to ultimately close. Again, they're single-gated, as we saw earlier. But as long as they're open, then the membrane potential is going to be going below its resting membrane potential and will be near the Nernst value for potassium. But then as those channels close, then you're going to get a drift up towards the baseline of the resting membrane potential. So during this period here, it is possible to have or to effect another action potential, but since it's in a hyperpolarized state, that means you're going to have a greater input of energy to bring those to threshold to light off another action potential, because you have further ground to cover because you're starting off with a lower negative type of a start point. So I think that's fairly easy to understand. When we're talking about this piece of the relative refractory period here, again, you could have an action potential there, but it's going to take, again, more energy. And the reason that you have it there is because some voltage-sensitive sodium channels are in the resting state and some are inactive. So I'm just going to say some voltage-sensitive sodium channels. Okay, they are in a resting state. And what I mean by resting state, they're good to go. Okay, they have their inactivation gate is open, the H gate is open, the M gate is closed. They're ready to rock and roll. But at the same time, you have some voltage-sensitive sodium channels are still inactivated. So it's a mixed bag. So I don't have all of the voltage sensitive channels ready to assist me in an action potential. So again, you can get an action potential in this area here, but it's going to take more energy because I don't have the luxury of having all of the voltage sensitive channels ready for creating an action potential. So again, so that's your 2 parts to a relative refractory period. Again, take home message. Again, 2 different mechanisms, whether you're on one side or the other side of that. But the take home message, it just takes more energy to have an action potential when you're in a relative refractory period. But when you're in an absolute, that means it's just physically impossible to have another action potential because it's just completely in an inactivated state. Okay, so let's take on another topic here that's kind of interesting. We talked about TEA as being a chemical that will selectively inhibit voltage-sensitive potassium channels. We have another compound, TTX, the tetrodotoxin, and that selectively blocks voltage-sensitive sodium channels. So another tool in the neuroscientist's toolkit. This works similarly to just your regular local anesthetics, whether you're talking about Procaine or Tetracaine. Of course, Procaine is Novocaine. Any of the canes are going to be blocking voltage-sensitive sodium channels, and if you're blocking voltage-sensitive sodium channels in an axon, that means you can't have an action potential. If you don't have an action potential, that means it knocks out all sensory function, knocks out all motor function. In other words, the axon cannot function. And so it will numb up if we're talking sensory, like you would go in the dentist, but it also is a paralytic because motor signals cannot go down any axons that are innervating muscles for muscle contraction. So it just basically blocks the activity of the voltage-sensitive sodium channels. If you have that, you're not going to have action potentials. The TTX, though, it works in a similar way as the Procaine or the Tetracaine, as I said. It is found naturally. It's found in the ovaries. It's found in the liver, the testes, the eggs of the pufferfish. And the pufferfish is in some cultures, in some restaurants, it's a delicacy. People like to eat it. But it has a poison to it. So when you go to a restaurant that is serving pufferfish, the chef that is preparing the pufferfish has to be licensed, because if you don't know what you're doing and you prepare it incorrectly and you get some of the fish parts that have the TTX, you ingest it, you run the risk of either making yourself very sick or possibly dying, because again, it's a paralytic. Now, with these types of compounds, the muscle that I would be most worried about in terms of any type of paralytic effect would be the diaphragm. Yeah, it's sad if you can't wiggle your toe because it's paralyzed, but who cares? But if you're blocking the action potentials of the phrenic nerve, then you're obviously going to be in a period of respiratory arrest, and then you die. So that would be a major problem with these types of poisons. So it's something that one has to be careful when one eats. I've never had a pufferfish. I have never been tempted to eat a pufferfish because I just never know if the licensed chef that prepares it was having a bad day. So I don't like tickling the tail of that dragon, so I've never had it. But, you know, some people enjoy it. I will also note that the Northern American salamander also has the pufferfish as well, or not pufferfish, but has the TTX in it as well. And so that is, again, something that you would want to be aware of. Something that you may have heard of before is paralytic shellfish poisoning. and you'll see it referred to as PSP. When someone has paralytic shellfish poisoning, or PSP, they're at risk of dying, and they would die of respiratory arrest. And the mechanism for that is from a diatom. You read about diatoms in your freshman biology. And this is saxitoxin. And saxitoxin is from the diatoms. And it is these diatoms that causes the red tide. And you probably have heard of the red tide before. The toxins, the saxitoxin, what it does is it blocks voltage-sensitive sodium channels. And so the effect is the same. So what happens with the shellfish is that the shellfish eat the diatoms, which is loaded with saxitoxin, and then it becomes part of the shellfish, and then you eat the shellfish, and then you basically have ingested this toxin, and again, you run the risk of having a paralysis, or at least paresis, a weakening of the diaphragm, bringing into jeopardy normal respiration. Okay, so again, some toxins here dealing with things that occur in nature that can actually block your voltage-sensitive sodium channels. Let's move on to another thought, and the other thought is having to do with changing the concentration of the electrolytes and how that might affect your resting membrane potential for a cell. Now, you will recall that the resting membrane potential is going to be a function of the Nernst values for the electrolytes. And we know that the dominant electrolyte is the concentration gradient for potassium, because the membrane is relatively permeable to potassium relative to sodium, as you see. So potassium is the major one that's going to set the resting membrane potential. So that means then, as I alter the concentration gradient, I would then am altering the Nernst value for potassium, because you recall the Nernst value of potassium has you plugging in the potassium on the outside of the cell and the potassium concentration on the inside of the cell. So, again, we're just going to go through it, just kind of a silly little example just to show what I'm talking about here. Suppose you slowly increase the potassium concentration outside the cell. What would happen to the resting membrane potential? Well, we saw in kidney where we have situations where you have hyperkalemia and hypokalemia, and we all understand now how important aldosterone is, how the kidney is in regulating potassium levels, because potassium is the driver of resting membrane potentials of all your cells in your body. So imagine that you have, let's just say, potassium, and let's just say that the outside concentration of potassium, we'll call it 4 millimolars, and the inside the cell, we'll call it 135 millimolar. So let me correct that. 135 millimolar. Okay, and so if you worked the Nernst value, you would find out with these concentrations that the Nernst value would be minus 93 millivolts. So that would be where the potassium wants the membrane potential to be, if I'm talking about those types of concentrations. So, fair enough. So what if I'm going to go ridiculous on you now, and I'm going to say, what if I change the potassium concentration from 4 to 40. Now again, that's not life-sustaining, but I'm just dealing with round numbers here to make a point. And I also hold it on the inside to be 135 millimolar. So now I have a tenfold increase in the potassium concentration on the outside. If you plug that into the Nernst equation, you would find that the new Nernst value is going to be minus 31 millivolts. So you can see what a huge difference it would make on the resting membrane potential of cells. So this is part of the reason why it's important to regulate or to tightly control the electrolyte distribution inside the cell versus outside the cell, because of the changing Nernst values and its impact it would have on the resting membrane potential. So what would happen, I suppose, that if you slowly increase the potassium on the outside the cell, the membrane potential will start creeping up, and then it would be approaching the minus 31 millivolts. Of course, you understand, I understand, there are a lot of other pumps and leaky channels that are, that are influencing the resting membrane potential. But all my point is that the resting membrane potential would become less negative. It's really all I'm saying here. Well, that sets me up for the next concept, which is accommodation. And with accommodation, during slow depolarization, which is exactly what we're talking about here, if I'm just gradually increasing that potassium concentration on the outside, if I have a slow depolarization, voltage-sensitive sodium channels are activated and deactivated without a membrane reaching threshold. In other words, I am having a depolarization event without having an action potential. So if you'll go back to a point that I had made earlier, and I've made, I think, several times, and that is to have an action potential, I need a large enough number of voltage-sensitive sodium channels opened at the same time. And if I don't get them opened at the same time, I could end up having the voltage-sensitive sodium channel become inactive without having an action potential. In other words, it would never reach threshold. And of course, threshold by definition means having an action potential. So to make my point, I'm going to go and use some ridiculous numbers, but it helps to understand. Okay? So suppose, I'll write this out for you. Suppose that I have a voltage-sensitive sodium channel, and they have, say, different set points. In other words, I'm calling the set point being the point where they will respond to a change in potential. And so let's just say I have 4 of these in a line. So I've got one channel, and he's going to open up at minus 65 millivolts. That's his set point. I have another channel, and he's going to open up at minus 60 millivolts. And number 3, we're going to say minus 55 millivolts. And number 4, we're going to say minus 50 millivolts. So we got 4 different channels, and they're all opening at different potentials. Now, let's just say that these channels, this is where it gets crazy, these channels are open for 1 second, okay? Which you know is impossible. Just say, so they're open for 1 second. So for 1 second, okay, both H and M gates are open, which means sodium can flow through. But it only lasts for 1 second. Okay? Now, let us also stipulate or assume, in my little crazy make-believe world here, that for me to have an actual potential, for this situation to reach thresholds, I have to have at least 3 of those channels opened up at the same time. So there has to be some time frame where I'm getting flow of sodium into the inside of the cell through at least 3 channels at the same time. Okay? If I don't have that, then I can't have a threshold. Now, again, I'm making this stuff up. Okay, the 3 channels, I'm making that up. But again, I'm just trying to make a point. Okay, so we know 2 things that are ridiculous. 1, that they're open up for 1 second. 2, that I got to have 3 of them open at some point to allow sodium to come through all 3 at the same time. At some point. Okay. Now, suppose that I slowly increase the potassium level outside the cell. So I'm going hyperkalemic. And suppose it goes up and up and up. I'm going, say, from my normal minus 70 millivolt resting membrane potential. So I'm increasing potassium on the outside, and then finally the membrane gets to, say, minus 65 up here. So what happens to this channel here? Well, when I hit minus 65, it opens, stays open for 1 second, then closes. But my elevation of potassium is so slow that I'm not going to get to the minus 60 resting membrane potential level for another 2 seconds. So by the time I get to minus 60, the minus 65 has already opened and closed. And so now I hit the minus 60. It opens, stays open for a second, and closes. And then it takes me 2 seconds to get to minus 55. It opens and closes. And then minus 50, 2 seconds later, it opens and closes. So what I've done is I have increased the membrane potential or depolarized it so slowly that at no given time did I have more than one of those channels open simultaneously. So I was able to increase, but slowly enough to where I never reached threshold. And then what happens is once I've reached, say, minus 50 or so, minus 50. So now that is the new resting membrane potential. New resting membrane potential. Or let's just say minus 40. Minus 40 new resting membrane potential. Then what has happened to all of these voltage-sensitive sodium channels? They're deactivated. The inactivation gate, the H gate, is closed, and it will not open because it has not seen a minus 70 resting membrane potential. So I basically have removed those voltage-sensitive channels to where they can no longer do anything as long as the membrane is sitting in its new resting membrane potential of minus 40. And so this is what we call accommodation. Now, of course, if you had a rapid increase in a depolarization, in other words, suppose we go back to normal. All right, going to my little make-believe here, I'm sitting at minus 70 millivolts. And then I have an action potential. Maybe I'm having some neurotransmitters binding to sodium channels. They allow a lot of sodium in, and I have a very rapid increase in the potential, or a rapid decrease in negative or an increase towards the depolarization, such that it zips through 65, 60, 55, and 50. It goes through all of them in a half a second. So now I've got a very rapid increase because I'm dumping a lot of neurotransmitters onto that postsynaptic terminal, allowing a lot of sodium to come in, causing a rapid depolarization. So those voltage-sensitive channels that are near that synaptic terminal will experience a very rapid depolarization. So if I can get through going from minus 70 to, say, minus 40 in a half a second, would you not see that there would be a period of time where all of these are open simultaneously? And so I can allow sodium to come through, and therefore what we were saying is that if I can have at least 3 of them open at the same time, that's enough to bring the whole system to threshold. Then all of these channels are going to start affecting other voltage sensitive channels in the neighborhood, and now I've started my chain reaction. So again, this is what accommodation is like. So you can slowly increase the potassium to the point you're basically causing a lot of your tissue, your excitable membranes, to no longer have an action potential because you brought them beyond what they can do because they're all sitting in an inactivation state. So on the flip side of this, where we did raise the potassium level, could you not see if I went the other way and caused a reduction in potassium, that if you recalculated the Nernst value, that makes the Nernst value to be even less, right? Less than what it would be here. So that would in turn cause hyperpolarization. It would be more negative. And you'll recall in the renal block, I had mentioned that hypokalemia leads to hyperpolarization. And if I have hyperpolarization, I have yet again made it harder to have an action potential. So again, I mean, if you are lowering the the potassium concentration, you're making it harder. If you go through accommodation by raising it, you're making it harder as well. So one last point before we end this block, and that is when a patient, let's go back to hypercalcemia. So if you have a patient and they are having a gradual elevated level of potassium outside the cell in the body fluids, you have, in a sense, paradoxical clinical presentations in the sense that the first stages of hyperkalemia is going to be hyperactivity and spasms of the muscles. Then as it progresses, the patient will go from having spasms and kind of a hyperexcitability of muscle fibers to muscle weakness, where now you're having a hard time having action potentials in many of those muscle fibers. So why would you have both? Well, follow the logic or the reasoning, which is when you start off with elevated levels of potassium, you are causing the membrane to be less negative. And so if it's a slightly elevated bump, say you go from a resting membrane potential of minus 70 to a resting membrane potential, say, of minus 67, okay, just a slight uptick. You're actually going to cause or make it easier to reach threshold because you're nearer to the set points of those voltage sensitive sodium channels. It's easier to reach threshold because you don't have to go as far to get into those set points of those voltage sensitive channels. So you're making it easier to have an action potential. So if you depolarize just a modest amount, then you're going to cause hyperactivity of muscle fibers, and they will again be prone to spasms and just uncontrolled twitches because you've made them hypersensitive to having action potentials. because you've inched the resting membrane potential closer to what you have to get at when you want a depolarization or a threshold. So that's the initial response, is going to be muscle spasms and twitching and things like that. But then as it gets higher and higher, the potassium, that means the cell membrane gets less and less negative, and now you go from a hyperspasmic type of muscle activity because of the elevated potassium levels outside the cell relative to inside the cell. Now you're getting into accommodation, where it gets so less negative that you're now beginning to shut down those voltage-sensitive channels and making it actually harder to have an action potential in a muscle fiber or nerve fiber. So the symptoms for elevated potassium levels, hypercalcemia, start off being overactive muscles and nerves, and then accommodation kicks in, and you move then to being hypoactive in terms of muscle fibers and nerve function. So it's an important concept clinically. So just trying to explain or help you understand some of the concepts behind what you would see in clinic relative to the abnormal levels of potassium. One other thing before I end, propagation. And we've spoken of this before. But propagation is a sequential generation of new action potentials down a nerve fiber. Because of the size and shape of the action potential usually does not change, only the variation of frequencies of action potentials can be used to code for information transmission along the axons. So let me unpack that a little bit. Think in terms of neurons, and you've got, of course, billions and billions of neurons, and then they're making thousands and thousands of connections, which gives you trillions and trillions of interconnectivity, of course, because you got a multiplier effect. And as I've said before, action potentials are all or none. It's sort of a lie, but let's just roll for that now. So what that means then is how the nervous tissue is interpreting a signal. Really, the only grammar that the neural tissue has to communicate with is in terms of action potential frequencies. So if a frequency is increasing or a frequency is decreasing, that will then be processed differently within the central nervous system. And so whether you hear a loud sound or a soft sound, if you're talking auditory, if you're talking cranial nerve 8, and your cochlear mechanisms, and then the ensuing signal going into the brainstem. A louder sound in some of the hair cells would create an increase in action potential frequency. A softer sound, a decrease in action potential frequency. But that's how it gets all processed in our higher order cortices, as interpreting it as a loud sound or a small sound or a slow sound in terms of volume. It's just an example that the only currency, the only grammar that neurons can talk to other neurons is just simply a series of increasing and decreasing action potential frequencies. And when that happens, then you experience something different. So the action potential frequency is just bedrock for how neurons talk to each other and how they're interpreting each other's activity. Another last point that I want to leave you with before I end this section is that the maximum frequency is limited by the duration of the absolute refractory period, which means then my absolute refractory period is about a millisecond. Okay, so we saw that on the prior page here. So there's a millisecond there. Okay, so this is milliseconds. Which means then that's the limiting factor for what the frequency of an action potential is. So if the minimum time for the action potential is a millisecond, and milli, of course, is 1,000. So that means theoretically the best you're going to do is 1,000 action potentials per second. Now, I don't think that really rarely happens, but that would be your upper boundary. So it does give you then a sense of what you can do for action potential frequencies up to, again, 1,000 per second, although I think it's a little high, but that's close enough, I would think, with that. And I think I've said before that because of the distribution of the electrolytes, and when we talk about the sodium potassium ATPase pump, kicking out or bringing in potassium and kicking out sodium, it's not the case that an action potential happens and then before that next action potential can occur that you have to wait for the sodium potassium ATPase to redistribute the electrolytes, in particular the potassium and the sodium. That's not how it works. You could poison all of the sodium potassium ATPase pumps, maybe Wabane or something like that, just shut them down. You would have a reasonable amount of time where you would have action potentials continuing on, because remember, you have picomolar amounts of electrolytes that go through the membrane to effect an action potential, so you have a lot of wiggle room. So the only way that shutting down the sodium potassium ATPase pumps is going to influence action potential events is when you shut it down and you have enough action potential frequencies where you begin now to disturb the ion distribution of sodium and potassium to the point it begins to make a difference in the Nernst value. Now that's a lot of redistribution that would have to happen before that. But if you were to permanently shut down your sodium potassium ATPase pumps, yeah, eventually you're no longer going to be able to have an action potential because you're redistributing the electrolytes, upsetting the resting membrane potential, etc. But I guess my main point is that while those pumps have to be churning over the long term, it is not a situation where you have an action potential and then the pump has to turn to redistribute the electrolytes and another action. No, things happen much more rapidly than that. So anyway, I just wanted to disconnect, or at least not make sure you don't believe that the sodium potassium ATPase pumps, one turn equals one action potential frequency. You can shut those pumps down and you can have action potential frequencies for a fairly lengthy time, in biological time, we're talking a few seconds, before the lack of that activity of those sodium potassium ATPase channels would begin to alter in a measurable way the ion distribution across the cell membrane. Anyway, so we will close this one up here. See you next time. This next block I want to talk about and consider conduction velocity. I think you have an intuitive understanding of that. It's basically how fast the action potential is propagating down an axon or across an excitable membrane. Some principles we need to be aware of: the speed or the velocity by which the potential is changing, the action potential is going down, say the axon, is going to be in part a function of the diameter of the axon. So the greater the diameter of the axon, the greater the conduction velocity. So there's a link there between diameter of the axon and how fast that action potential can actually propagate down that. So I want to just basically touch on a few principles of physics that would inform us in understanding that. And one of the useful things or useful ways of thinking about this would be called the cable theory of an action potential. This actually began in the 1800s when scientists and engineers were trying to develop a mathematical model for signal decay in underwater telegraphic cables. And so by analogy, the idea could be applied to a theoretical tube made of a cell membrane and submerge it into a salt solution like fluid, and then measure the propagation of charge throughout this model of a tube of a cell membrane. So, don't get freaked out about all the squiggly lines and circles and stuff. It's not that bad. So, what we're doing here is we are measuring current. So we have amperage, in and out and such. So what we're looking at here is we have in a when you have an action potential, of course, you're moving sodium. Sodium is flowing in. And you have two flows of current. So I'll write that up here. Two flows of current or amperage. One flow of current you would already know, and that's the sodium going into the cell itself. Okay? And so that would be, let's just try and draw it down here. So you have, say, my tube there. So you know the sodium is going to be crossing that. So that would be one current. It would be going across the membrane. And so you would have certainly a certain resistance that is associated with that membrane. The other thing that you would want to be aware of, okay, we're just going to call this Rm. That's the resistance across the membrane. Well, sodium is going to cross the membrane, of course, but it doesn't just cross it and sit there. Okay, it's just not going to cross and just sit there. It's going to diffuse. So this would be better drawn with this. We would say that the sodium is going across the membrane, and then it is going in that direction. So now, not only do I have a transmembrane flow, I have a current down the actual axon. In this case, this direction and that direction. So the metaphor that I think about with this, if you can imagine that you have say a pool or a bowl of water, shall we say. And the bowl of water is placid, it's just still. And then you take a small drop of Indian ink. You know, Indian ink is very black. So you take a small drop of that Indian ink and you just let it drop onto that bowl of very still water. Well, as soon as that Indian ink hits the water, you know what you're going to see. You're going to see that Indian ink is just going to radiate out around the initial point. Now, how fast it radiates out would, I guess, be a function of the resistance of the Indian ink as it goes through the water. So imagine that sodium going into the axon is sort of acting like the Indian ink, that it's going to go in and then it's going to radiate out. Which means then is you could also speak in terms of having a resistance relative to the longitudinal distribution of the sodium flowing in, and we would just call that resistance L for longitudinal. So I have a resistance and a current associated across the membrane. I have a resistance and a current associated with the longitudinal direction. So this is sort of what we're talking about here by, again, longitudinal versus across a membrane, you see. So where this comes into play is that the increase in the diameter of the cable itself or the tube itself, or in this case, maybe the axon, that a greater current longitudinally is going to be a function of the diameter. So larger diameter gets me a lower longitudinal resistance, which means then the current can flow longitudinally more easily. So that's one of the factors at play tying conduction velocity to the diameter, is it has a significant impact on the longitudinal resistance. the increasing diameter doesn't do much for me in terms of across the membrane, because the membrane doesn't care how large the axon is diameter-wise, but once it gets inside the axon, it does when you're talking about longitudinal current. So that's kind of a tie-in to a cable theory of action potential and how the diameter is going to be influencing the speed with which an action potential propagates. Because obviously, if I have a lower longitudinal resistance, that is going to facilitate a longitudinal progression of the action potential itself. So that's a tie-in here. Okay. Let's talk about myelin. I believe you've all had freshman biology. You've had a sense of what myelin is. It's an insulating compound. It's actually a very complex biological compound, but a compound nonetheless. We call it myelin. We have two types of cells in your body, in your nervous system, that can make myelin. One is the Schwann cells. The other are the oligodendrocytes. And again, this is freshman biology stuff. You know that the Schwann cells make myelin and are associated with axons in the periphery nervous system, or peripheral nervous system, and that the oligodendrocytes are the ones that make the myelin associated with the central nervous system. And so these oligodendrocytes and central, or the Schwann cells and peripheral, are intimately associated with the axons themselves. And also, you'll recall from your freshman biology, you already know that a myelinated axon is a faster propagation of action potentials than an unmyelinated axon. And so I want to explore a little bit as to why that would be the case. So again, I think you recall much of this anyway from earlier courses. And imagine that we're just saying, okay, this is the myelin here. Okay, myelin, myelin, myelin. And this is an axon, of course. So it's just a myelinated axon. And then we have areas of the axon that are unmyelinated, and we call those the nodes of Ranvier. So there would be a node, and there would be a node, and of course there would be a node. These nodes tend to be 1 to 2 millimeters apart from each other. So 1 to 2 millimeters in distance, thereabouts. So when we have the myelin, it's an insulator. So that means it greatly taps down the flow of electrolytes across the membrane. So deep, the axon that is wrapped by the myelin, the sodium and the potassium just can't cross the membrane very well at all. So what that means then is that, and I'm going to tie this in a second, that the presence of myelin is going to increase my length constant. Oh, there's that concept again. Length constant. Remember we talked earlier about what caused the diminution of the effect of the electrical field down an axon? Well, it was because as I moved further away from the electrical field caused by the battery, I easily had an efflux of potassium, because if the battery is holding the membrane at plus 50 millivolts, that's very far away from the Nernst value for potassium. So potassium is going to leak out and begin to try to fight the battery. And the farther away from the battery you get, the more success the potassium has to efflux and bring the membrane closer to resting membrane potential. Well, the challenge for an axon that is myelinated is the potassium can't cross the membrane very well at all. So what that does is that lengthens the length constant. In other words, it takes the effect of the battery, if we're going to go with that analogy, and now the influence of the battery is longer down the axon because I have insulated it. I'm not allowing the potassium to fight the electrical field because the myelin won't let the potassium out. So I have lots and lots of voltage-sensitive sodium channels in the nodes. It doesn't make sense to have many voltage-sensitive channels under the myelin because there's nothing really for them to do, although you do have a few. But concentration of voltage-sensitive sodium channels, and then I have lots of concentration of voltage-sensitive potassium channels as well. Let me rewrite that better. Voltage-sensitive potassium channels, and they're going to be here as well. And I am going to have, again, voltage-sensitive potassium channels on the edges too. Okay, they tend to fizzle out as you get too far in the myelin, but you have that. So now, what happens is that, let me go ahead and put them here too, there, and we'll go here, get back to my red, and so they're there. Okay, so what would happen is that if I were to have a depolarizing event, say an action potential, and so now I'm having my action potential at that node right here, and because I have the myelin and it extends the length constant, okay, so now I have a greater effect over a greater period, a greater length, all I need to do is if I have an action potential here, I need the potential to change in the node downstream to bring it to threshold. So the object of the game, if I have an action potential here, I want that depolarizing event to be such that it can bring this node to threshold, which means I have to have a long enough length constant such that whatever effect is here, you can bring that at least to threshold here. And of course, that's exactly what happens. So I have an action potential here, which will bring this to threshold. And then it will have an action potential, which will bring this to threshold. It will have an action potential, and so forth, so on. So I'm literally leaping from node to node to node. And the key here is the ability of the myelin to extend or give the axon a greater length constant. So this is called a saltatory conduction. And of course, saltare is Latin for to leap. So this process of leaping from node to node to node is extremely fast, much more fast than if I had the same length of a axon that was not myelinated and I had all these voltage-sensitive sodium channels going through there, where it has to go from channel to channel, channel, channel. That's a much slower process. So the sleeping is, by several orders, much quicker. Now, another question that you would raise would be, if you thought about it long enough, let me clean some of this up, and that would be, if I have an action potential here, so if I have an action potential here and then have an action potential here, now of course this action potential over here then goes away, why doesn't that action potential kick back in both directions? And I think you probably know the answer to that. And that is that while I'm having an action potential here, that this area here is an absolute refractory period. So it can't go backwards, because if it's an absolute refractory period, that forces the propagation of the action potential down the axon. Now, of course, if I took an electrical probe and found me an action potential that was myelinated and put my probe here and then depolarized it, well, then, of course, I'm going to have an action potential propagating in both directions, because the nodes on either side are not in absolute refractory period. But if I'm going normal down the axon, then the action potential propagation is only going to go in one direction, you see. Okay? Another thing that's useful with this is that because I have just narrow areas of voltage-sensitive sodium and potassium channels. I utilize much less sodium and potassium movement to get a propagation of an action potential compared to a non-myelinated axon, because I have fewer voltage-sensitive channels that are doing the trick, which means that I don't have to expend as much energy by the sodium-potassium ATPase pumps because I have much less sodium and potassium to move in and out. So this is very energy efficient. Okay, and I think I made the point last time about that with the sodium ATPase pumps, that I'm not needing a pump to turn for every one action potential. Again, I have a lot of wiggle room with that. Another analogy in terms of thinking about movement of electrical current down a tube. Again, it may or may not find this useful, but if I were to have a hose and I'm running water through it, of course the water is going to go through a certain velocity. But what if I had a hose that had lots and lots of holes in it to where the water was squirting out of the hose in 15 different directions? That would in fact decrease the flow of the water down the hose. So, it's just another way of looking at it, I suppose. One other clinical point here I want to make while I'm talking about myelin and such, and that is multiple sclerosis, or MS. We all know what that is. So multiple sclerosis is an autoimmune issue where my immune system is stripping away the myelin from the axons in the central nervous system. Again, this is not a peripheral nervous system issue. This is a central nervous system issue. And so you can certainly imagine that MS, your immune response involved in that. Not only is it stripping myelin away, it's also killing oligodendrocytes. And so when you're in the throes of multiple sclerosis, you have this kind of push-pull because your central nervous system does have some regenerative capacity, in the sense if you strip the myelin away, then your oligodendrocytes are going to multiply, they're going to proliferate, and they're going to try to remyelinate it. But so now you're having this back and forth of stripping away, remyelinating, stripping away, remyelinating. Eventually, the multiple sclerosis is going to win, but it is a fight. So you can imagine if you have an axon and you start stripping away the myelin, okay, myelin, and then all of a sudden I'm starting eating away at it. Obviously, what that does is it impedes the saltatory conduction down an axon. If you were to strip away great areas of it, actually what would happen would be that you would get some redistribution of the voltage-sensitive channels, and you may have some conduction down the axon, although it would be very abnormal. It would be abnormally slow, so it would not be anything that would be, it's not behaving as if there was myelin there, which then means as to why you have so much involvement in terms of movement disorders or muscle function as a result of the multiple sclerosis. The other thing, too, is as a phase of this stripping, is that, as I mentioned, you do have quite a bit of, let's see, I think I was going green for the voltage-sensitive potassium channels. It begins to expose excess voltage-sensitive potassium channels over and above whatever voltage-sensitive sodium channels are there. You seem to have an excess of the voltage-sensitive potassium channels. And if you're exposing more of them, that makes it even harder to have action potentials because you have a disproportion of voltage-sensitive potassium channels relative to sodium channels. So that perturbs the situation as well. So I guess I don't want to get too much in the weeds in terms of the mechanics. It's a fascinating literature to read about. But I guess what I'm trying to say here is that the stripping away of the myelin because of the multiple sclerosis is certainly going to cause a significant perturbation of axial potential activity on a axon to the point that it just basically you can't have one. And if you've ever dealt with somebody who has MS, they'll have good days, they'll have bad days, because again, you got this push-pull. You got your immune system trying to mess you up, but then you're having the regenerative capacity of your nervous system trying to repair what the immune system is tearing down. And again, it's kind of a back and forth. Let's take a look at the diameter effect of axial potential frequencies. I think this is pretty cool. Kind of a classic drawing here. So we have a myelinated axon from a cat, and then we have an unmyelinated axon from a squid. So the trick in understanding, and this is conduction velocity, meters per second. So the trick in understanding this diagram is to understand which x-axis is going with which line. So let's clear this one up very quickly. So this line here, okay, it applies to this axis here. And we'll go a different color. This line here is applying to this axis here. So I hope the color can help you out in terms of keeping things straight. So with that bared in mind, an unmyelinated axon, again, diameter. Now again, I want to go blues here. The diameter of the unmyelinated in microns. So note the scale here. So we're talking unmyelinated, we're talking 0 to 200 to 400 to 600, 800. That's huge. So we're talking huge diameter. So the trend line, obviously, and the little dots are data points for actual measurements, that you can see the trend as you go from, something near 0 on up to 800, you're going to get an increase of velocity of the axial potential down the axon. So maybe down here, maybe that's 4 or 5 or something like that, meters per second. And then it kind of tops out. We're talking what here? Well, that little bit, there you go, straighten it out for me. We're talking, I don't know, maybe upper 20s. For meters per second. So that's kind of your range from maybe 5 or so meters a second to upper 20s meters per second. But that's with a huge diameter for an unmyelinated axon. Now let's shift our gears a little bit and consider what's going on with the myelinated axon. So now we have a complete different change of scale. Now we're not talking about hundreds of microns. We're talking about an individual micron, you see. So we're talking up here, we're talking maybe 12-ish microns. So 12 microns on the unmyelinated, it's almost like you can't even see it. But 12 microns here. And so note again, as you go from, say, 2 microns to 12 microns, the huge difference we got here. Okay, we're in maybe the teens for meters per second, all the way up here. Now we're into, wow, maybe 100 meters per second. That's a huge increase in velocity just by increasing from 2 to 12. So we're having extremely small diametered axons, but you'll also want to compare that the fastest unmyelinated is here on the myelinated. So again, you see the difference in what a profound, again, both of them are showing that the larger the diameter, the greater the velocity, but you see how different and how profound the myelination and that saltatory conduction has on a velocity of an axon down, or action potential down an axon. So again, let me make this point again. I sort of made it earlier, but let's rethink this. You have 2 ways of increasing the speed of an axial potential down an axon. So I'll write that down for you. 2 ways to increase velocity of action potential down the axon. 1 would be to lower the resistance of the longitudinal resistance. Lower. I'm going to go RL. Lower the longitudinal resistance. That sounds pretty obvious, I think. And how do you do that? By increasing the diameter. Increasing diameter. And you recall from physics that is it not the case that a large diameter wire made of a certain material is going to have less resistance than a small diameter wire of the same material? Again, cable theory. So by increasing the diameter, I'm lowering the resistance longitudinally. So that would increase the velocity, of course, down the axon. The second way is to increase the resistance of plasma membrane to current flow. I'll explain that in a second. So increase resistance, okay, across the membrane to current flow. And they say, wait a minute, if you can't have current flow across the membrane, you can't have an action potential. That's true. But what I'm referring to here is the increasing the membrane resistance to current flow by using myelin. So now we're back to the nodes. So I'm wanting to increase the resistance of the membrane here, and here, and here, and here, setting myself up for a saltatory conduction. So that's what I mean by increasing the membrane resistance. I'm doing so with the myelin, but I still have to have the nodes of Ranvier to make that work. Okay? All right, so let's go to another concept here because I want to return to the idea of length constant, and I want to get a little more detailed in that idea. And don't let the squiggly lines intimidate you. You saw these kinds of things in your second semester of physics. Here, again, familiar concepts here. I've got resistance membrane. Okay, that's my RM. And then I have resistance longitudinally, so it's resistance L. Okay, so I'm talking about that direction and then across the membrane. That's all I'm meaning here. So that's fine. Of course, capacitance is my cell membrane, electrostatic forces. Okay. So here's a new aspect to all of this. And I'm going to introduce you to tau. We're going to see tau a lot in the rest of the course, but I want to soften you up to that idea. Tau is usually associated with some type of time constant. And then the second thing is going to be the length constant, which we've already talked about, also known as space constant. And we're going to let lambda represent length constant, and we're going to let tau represent time constant. Now, the lambda length constant we've talked about. Tau we have not, but we're going to now. And I'm thinking the best way to introduce you to the concept of time constant, and then we're going to build on top of this to connect that with length constant, is to go with an analogy. So I like this. I think it's easy for you to understand. So here's my analogy. Think about that I have a block of metal. I have a cube, and it is metal, so it conducts heat fairly well. So I've got a solid cube metal. Now imagine that I have a hot plate. Imagine that the metal is sitting out in the room. Let's just say it is 10 Celsius degrees. Imagine that the hot plate is 100 Celsius degrees. So if I take that metal cube and place it onto the hot plate, of course, you know what would happen. After a certain period of time, the small cube on top of the hot plate would become the same temperature as the hot plate. I think we know that, yes? Anybody that cooks on a stove knows this. But you also know that the cube, once set on the hot plate, it doesn't become 100 degrees instantly. It takes time. And so this is where we want to introduce the concept of a time constant. By nature of the metal cube itself, how long does it take for that cube, that metal cube, to be identical to the temperature of the hot plate? So I think that's something we can, of course, understand. Now, if we go to a neuron or an axon, and we have a resting membrane potential, and then we depolarize the membrane, you know and I know the depolarization does not happen instantly. It happens fast, but it doesn't happen instantly. In other words, there is a time involved in the sodium coming in, altering the membrane potential. So if we had a recording electrode measuring a resting membrane potential of minus 60 millivolts, and at some point time 0, we turn the battery on, that's going to depolarize the membrane, then at that time it's going to take a certain amount of time for the sodium to come through. So despite the fact that the stimulus changes instantly, the change in the potential does not occur instantaneously. It takes time for the potential to change from its initial value to its final value if I want to take the battery and turn it up to, say, minus 50 millivolts. So we're not talking now about causing an action potential in this particular example here, although it applies to that. All we're talking about is how long it takes that battery to effect a change in the potential of the membrane itself. We can measure it. It's not instant. Okay? So, and we're going to tie this to time constant. So all I'm saying here, whether it is taking a battery and changing the potential in a membrane by turning a switch on, or whether it is changing the potential of an axon by influx of sodium, all I'm saying is it's time dependent, and I don't think that should be a shocker to you. It's fast, but still we can assign time to it. And we would call that tau, and we would call that time constant, how quickly things happen across the membrane. Okay, so that's that. Now let's flesh this out, flesh this point out in a more detailed way. Here we go, more time constants. So there is a convenient index of how rapidly things change with time across a membrane. And again, we're going to use tau, called time constant. Okay, here's the verbal salad. It is defined as the amount of time it takes for the change in the potential in a capacitor to reach 63% charging or 37% discharging of its final value. Now here we go again with the funky 3763, and you'll note that 63 plus 37 gives me 100, so percentages wise, So, and again, I will remind you that these figures here are tied to the value of E, because inverse of E is, of course, this. So again, we're using capacitor, discharging and charging of a capacitor as an example, but you can quickly, easily apply it to a cell membrane because a cell membrane is capacitor. So what we're talking about here then is we're just going to link these two here. Okay, we're thinking about a capacitor here. So imagine that I have something down here. This one down here, suppose that is a battery. Okay, so I've got a battery source here, and I am turning it on, and I'm turning it off, say in milliseconds. So I've got the battery putting energy in the system at 100% for just a 0.5 milliseconds. So now I am measuring the capacitor potential across that capacitor here. And so again, these are percentages. Okay, so this is going to be 100%. So as I take the battery, I put energy in the system, how long does it take for that capacitor to charge? Okay, so I start here. Okay, that's the time where I flip on the switch, and then it's going to be a curve. It's going to be up, and then finally up here, it has reached 100% of separation of charge, complements of the battery putting energy in the system. But you understand this wasn't instant, it was a curve. And so what we would want to do, and this is time to charge, time to charge the capacitor. And so what we would say, then whatever time it took to bring the capacitor to 63% of what it's getting to, starting from its initial point, that is tau. I will write that in a different color just to be emphasizing it. Okay, this time point here, that is tau. So tau is going to equal a time. And whatever tau is, that's the time it took when you're charging a capacitor to get to 63% of its final charge. Now, when we're into discharging, so now we're turning the battery off, and so now the capacitor is going to drop its separation of charge because of its nature. So again, that doesn't happen instantaneously. It'll start here, and it will go down. So we want to know how quickly, because of the nature of the capacitor, what's its tau? In this case, it's 37%. So now for discharging, tau is when it is reaching 37% of what it was, and so that would be the tau for discharge. So you can have a tau associated with a capacitor that is time to charge, is a tau value, and time to discharge is a tau value. And you'll also note that this curve and this curve are very different because, again, it has to do with the nature of the capacitor itself. So we can apply the same concept to a capacitor we call a cell membrane in terms of how quickly things change, and that 63% is very important. So the time constant, again, is a function of two properties of the membrane. It is a function of the membrane resistance, okay, and then the membrane capacitance. So you recall those are two different things. So the membrane resistance is how hard it is for the charge to cross the membrane, and then the capacitance is how well does the membrane separate a charge. And so we have a formula where tau is going to equal to the product of the resistance of the membrane and the capacitance of the membrane. So I don't want you to get lost in the weeds on this. So all I'm really saying here is the take-home message, and this is the key point. Smaller tau means things happen faster. So that's the key take-home point that I'm trying to get across to you. When tau is larger, things are happening more slowly. When tau is smaller, things are happening more rapidly. So that's what I'm really trying to get at here. So I'm not wanting to bend your mind trying to figure out how that product is tied to that. I'm just saying there's a relationship there. There's lots of mathematics behind that. That's not the purpose of the course or the purpose of my lecture here. It's that you can quantify tau, and tau is definitely related to resistance of membrane and capacitance of the membrane. And you'll recall that the capacitance of the membrane, okay, it's going to have a relation of 1 over the diameter, where the diameter is the distance. You recall that from an earlier lecture. Remember, you have two plates, okay, and so you have a wider the distance, the lower the separation of charge, okay? And so I have a inverse relation. So the larger the distance, separation of the two plates, the smaller the capacitance. And you'll recall that from an earlier lecture. And basically, the myelin increases the distance. Therefore, the myelin reduces the capacitance. So, again, I'm going to bring you back to the main points that I'm wanting you to get out of this, which is understanding what tau is. And tau is a rate of change, and that it's tied to the 37 or the 37 or the 63 related to E. And again, my major point is smaller the tau, faster things happen. And you can see this up here. So this tau here, okay, again, it's tied to time. If the tau, let's just go up here. If the tau were here instead of here, then would not the tau be smaller? Which means then that things would have happened more rapidly, you see. So that's all I'm saying there. Okay. So now let's do a consideration of length constant. Okay. And so here I'm going to have another cool analogy for you, and we're going to go back to metal and a hot plate. So now we're shifting our gears from time constant, how rapidly things happen in the axon, to length constant, okay, what the effect is downstream in the axon. So here's my really cool analogy. Consider another thermal analogy. Take a long metal rod. I don't know, make it 10 feet long. It's metal. So now with this metal rod, it is going to be 10 degrees. And now I'm going to take that metal rod and I'm going to put it on the end, take the end of it and rest it on that hot plate. Now again, imagine, now the rod is 10 feet tall. And I got this little old hot plate down here, but I'm just going to take the end of that rod and put it on the hot plate. Now, the question is that rod going to at some point all be 100 degrees Celsius like the hot plate? I think if you think about this, you know the answer. The answer is no. That it is in all likelihood that while the rod that is right next to the hot plate would be 100 degrees Celsius, the temperature of the rod 10 feet away on the other end probably is barely different than what it was to begin with. Maybe it's 11 degrees Celsius, don't know. But I think you have an intuitive understanding that you're going to have a temperature gradient. That the farther away you get from the hot plate, the less the temperature change. So why is that? because the rod is not insulated, and so it can dissipate the heat. And so the farther away from the heat source, the less effect the heat source has on the rod, because you're losing the energy as it radiates out from the rod. Again, this is analogous to the potassium leaving the axon because of the battery that's some distance away, causing or lessening the effect of the battery. So again, how would the temperature be distributed on the length of the rod? There would be a temperature gradient. Again, we talked about this. The temperature gradient would be described as the exponential function of the distance between the physical processes involved. In other words, the hot plate and how far away the hot plate is going to be. So here's the kicker. As stated earlier, the Planck constant is the distance over which the potential change decreases to 37% of its maximum value. So now you can think of that in terms now of temperature change. And you can do the same calculation. Earlier we talked about Planck constant in terms of voltages. Now we can talk about it in terms of temperatures. So what you would do is you could say, and it's easily calculated, you could say, okay, this rod has a Planck constant. So that regardless of what the temperature is on the hot plate, whether it's 100 degrees Celsius or 200 degrees Celsius or 75 degrees Celsius, the rod is going to have one length constant, and it will be a length. And that length then will represent the 37% of whatever temperature change I have relative to the hot plate. And that will be constant. So it doesn't matter what the temperature is on the hot plate, that length, so I could say this rod has a certain length constant. So regardless of what the temperature change is, the 37% would be that mark. So how could I change the length constant of the rod? By changing the rod itself. What if I were to wrap that rod in styrofoam? What if I were to insulate that rod? What if I were to do something with that rod that keeps it from losing its heat or dissipating the energy? Would that not, in fact, increase the length constant? It would. Because now that 37% mark is going to be farther up from the hot plate because I insulated it, which means I basically have changed the nature of the rod. So that's another way of getting your mind around the concept of a length constant. So we will close this one here. We left off last time talking about this equation here, lambda, and it is a way of calculating a length constant. We had explored that earlier, and one of the things that you need to be aware of is, again, how the relationship between like resistance across the membrane and then the resistance downstream longitudinally is inversely related to each other. And so this is a good estimate for that. So again, it's important just to understand how these things are working. And also remember diameter. So the greater the diameter, the greater the Planck constant or the lambda. Okay, how are the time constant and space constant, or also called Planck constant, related to the propagation of the velocity of action potentials? And most of this you kind of already know. But the smaller the time constant, the more rapidly the depolarization will affect the adjacent area. In other words, things happen more rapidly. Obviously, it will go down either from node to node. If we're talking myelinated or unmyelinated, it'll still have the same effect. If a depolarization more rapidly affects adjacent areas, again, it will bring the adjacent area to threshold sooner. Therefore, the smaller time constant, the more rapid the propagation velocity. If the space constant is large, a potential change at one point would be greater distance along the axon and bring the distance regions to threshold sooner. Therefore, a greater length constant or space constant will more rapidly depolarize distant regions, which obviously then means I'm going to have a greater propagation velocity. Here's a cartoon that I like because what we're doing here is site of depolarization. So if we depolarize, at this point right there, we know that the potassium efflux in response to the depolarization is going to fight the depolarization. Because you'll recall if a potassium's length constant, a potassium's Nernst value, suppose that were, call it, say minus 88 millivolts. And if the membrane is close to that anyway, then there's not a lot of driving force to have potassium egress from the cell. But if you have a site of depolarization, so where now this is, plus 70 millivolts, now all of a sudden potassium is very unhappy, and so you're going to have efflux of potassium that's going to try to bring that membrane potential back down to where it wants to be. And you have a diminishing effect. The farther away, the less effect, but you're going to have, again, a longitudinal spread of outward flow of the potassium, and I think the vectors here do a nice job. So below this, though, you have how the length constant affects all of this, because if you have a small unmyelinated neuron, which is going to be here, okay, in both directions, if we please. What you have there, distance from the site of depolarization, you see that you have a shorter length constant. But if you are dealing with a myelinated, which would be, of course, this here, then you can see how the myelinated, you're going to have a longer length constant. In other words, the influence of the depolarizing event here is going to be felt at a wider span. And so that's just a nice graphic of showing how that would work. So putting some numbers on the conduction velocity, which we can do here. Conduction velocity is going to be proportional to, we got length constant and tau. So the one's in the upstairs, one's in the downstairs. And so conduction velocity, the larger the length constant, the faster the conduction. The larger the tau, more slowly things happen, the smaller the conduction velocity. So we've talked about separate equations about time constant and length constant or space constant. We can actually come up with another equation and say the conduction velocity is proportional to 1 over the Cm, okay, and that's going to be capacitance square root diameter, and of course you have the two resistances here. There's a way of deriving that equation. I'm not really interested in you doing that. What I'm interested in you understanding is a relationship of what changes relative to are they in the upstairs or the downstairs, and how that affects the conduction velocity. So you're going to note that myelin causes a decrease in the membrane capacitance, thereby decreasing tau. Tau decreases, conduction velocity is going to increase. We saw that up here. So again, we want to make sure we understand the relationship. If we have a drop in capacitance, then that is going to lead to an increase in the velocity. And if we have a drop in the membrane resistance, we're going to have an increase in velocity as well. I've made this point before in terms of how much sodium is going to be going across a membrane in response to a depolarizing event. And we know that it is in the picomolar amount. Therefore, it doesn't take a lot of activity for sodium-potassium ATPase to correct that. And again, I've also mentioned before that which is not the case, that if you have an action potential that the cell has to wait for the sodium potassium ATPase to remove the sodium and the potassium from the respective sides to have another action potential. You can have literally thousands and thousands and thousands of action potentials without any activity of the sodium potassium ATPase pump. But at some point, that is going to affect the cell dynamic. So if you magically poison the pumps, or you hit it with some Wabam or something, and poison the pump so you stop the sodium potassium ATPase pump, you're going to have a lot of action potentials before you start seeing the effect, because it's just such a small amount is involved in crossing sodium and potassium relative to an action potential. Okay, next page. I just want to spend a little bit of time on some clinical. I'm not going to read all this to you. You can read. We want to talk about multiple sclerosis. We all have a sense of what multiple sclerosis is. It is a demyelinating disease, typically is autoimmune, or is an autoimmune disease, and it is going to be working on the myelination within the central nervous system. So this is not a peripheral nervous system issue. This is a central nervous system issue. And we know that oligodendrocytes create the myelin from within the central nervous system. And so for whatever reason, the immune system decides to attack the oligodendrocytes. The path of the disease, the symptoms of the disease, very unpredictable. Typically an MS patient will have periods where they have difficult in motor function, and then they'll have periods where they don't, so it'll wax, it'll wane. In multiple sclerosis, you're going to see a decrease in oligodendrocyte number. So oligos, decrease in number. Also, what you got going on is your immune system is attacking the myelin, attacking the oligodendrocytes, but your central nervous system is always trying to fight back. And so in MS, you have the process of demyelination and remyelination occurring all the time, because the central nervous system is trying to fight back, is trying to undo the effects of the demyelination process. So there is a bit of a tug of war, and so it waxes and it wanes. Ultimately, the MS is going to win, but you know, it is what it is. Most people, the first symptoms they'll have in MS is between 20 and 40. The initial symptoms of someone who has MS is typically a vision problem. They may have diplopia or double vision, or they may have blurred vision, or they may have some color distortion, or maybe even blindness. And if somebody comes in to your clinic and they're 35 years old and no other symptoms, and all of a sudden they're diplopic, there are lots of things that could cause that, but one of the things on your mental checklist to at least consider is going to be MS. Most patients, again, muscle weakness in their extremities, loss of coordination, the usual stuff. The worst case scenario, MS can produce partial or complete paralysis. Most people with MS will exhibit paresthesias, and that's where you have the pins and needles sticking. I know you've gone to the dentist, and when the anesthesia wears off, it feels like, you know, there's a period where it's like pins and needles are sticking in you. Well, that's what that is. Some MS people, patients suffering from MS, will find the experience to be painful. You could have tremors, speech impediments, you could have vestibular issues. Occasionally, MS people would have hearing loss. Approximately half of all MS patients experience some cognitive impairment, difficulties in concentrating, holding attention, memory, poor judgment, etc. These tend to be rather mild, but they can be there. And depression is also another common feature with MS. So, but again, every patient is different in terms of how they're going to present. So there's no typical thing when it comes to MS. Varies wildly. The reasons that demyelination interferes with axon function, well, I think you can understand that. The link constant is shortened. The number of voltage-sensitive potassium channels near the node are exposed. Remember, previously the myelin was covering those up, so that certainly is going to lead to a shortening of the length constant. And again, those exposed potassium channels are going to be influencing action potential. Once the myelin is removed, the voltage-sensitive potassium channels and sodium channels are redistributed and alter normal function of the axon. Typically here with multiple sclerosis, I think we're talking about 30 per 100,000 population to give you a sense of its distribution. Sclerosis, as you know, means hard. This is what you'll see. Plaques form in the central nervous system. Multiple plaques can be found in the central nervous system. This is kind of a histological sign for this particular pathology, hence multiple hard areas or multiple plaques, and we got multiple sclerosis. Another demyelinating disease is Guillain-Barré syndrome, which is called GBS. It is sort of like the MS, except that it is attacking, or the immune system is attacking the peripheral myelinated neurons. The symptoms of the disorder include, again, varying degrees of weakness or tingling sensation. Legs, feet tend to be first, so your distal areas of your extremities. A lot of times you'll have, in many instances, you'll have symmetrical weakness and abnormal sensations spreading to the arms, hands first, upper body. And again, tends to start peripherally and then works backwards. So the symmetrical thing is important because if you come in, or a patient comes in and the symptoms are very asymmetrical, it's less likely that it's going to be a body-wide pathology. Body-wide pathologies tend to present in symmetrical side to side. So if I've got tremendous muscle weakness on one extremity compared to the other extremity, unlikely that it is a body-wide pathology. You wouldn't want to look to things that are specific to that side of the body. But if you have a body-wide, or if the symptoms are very symmetrical, then you want to look at some systemic issue that is working on the body. Oh, let's see what else we have here. Again, you always have breathing. Again, the axons involving the contraction of the diaphragm, that can be compromised. Of course, you'd want to put them on a ventilator if that's the case. Most individuals will have a good recovery, even in the most severe cases of GBS. So this is where there's some differences between this and multiple sclerosis. The GBS, most people will recover from it. Also, it is much less than MS, so we're talking 1 per 100,000 as opposed to, 30? So 30 times more MS than GBS. So that's one of the things that we would worry about. How do you get GBS? Again, a lot of times it's idiopathic, but many times GBS is going to be a function that is secondary to an initial infection. So it could be that an individual had an extremely virulent strain of influenza, and so they go through a severe flu case. They recover from the flu, and then a week later, now they're showing signs of GBS. So what people think has happened is that the immune system, for whatever reason, in its fighting off the flu, got sideways and started attacking the myelin in your peripheral nerves. Don't know why, but sometimes that happens. So a lot of times GBS is going to be secondary to an initial condition of some type of pathogen. But sometimes it doesn't. Sometimes it just happens. There have also been reports of GBS following when people had infections of Zika virus. Again, most not, but sometimes it happens as well. And on rare instances, vaccinations may increase GBS, but that is extremely rare, and it certainly is not a reason to avoid vaccinations. Anyway, you're going to see GBS in your practice. I'm pretty sure of that. The last one that I want to talk to you about is the Charcot-Marie tooth disease. In clinic, this is known as CMT. It is one of the most common inherited neurological disorders. Okay, so this is different because this is more genetic. It affects approximately 1 in 2,500. So if you do the math, it is fairly common. CMT is also known as a hereditary motor sensory pathology. Sometimes you'll see it as HMSN, or peroneal muscular atrophy. Again, other names for it, but commonly it's going to be CMT. And there are multiple kinds of CMT, so I don't want to imply that they're just one disease. There are different subtypes of this as well. But it's thought to be working on the genes that affect normal function of the peripheral nerves. So again, like GBS, it is a peripheral nerve issue. The peripheral nerves that of course, lay outside the brain and spinal cord, supply the muscles and sensory. Typical features include weakness of the foot or lower leg muscles, which may result in foot drop, and a high stepped gait with frequent tripping or falling. So the CMT, again, it tends to be feet to be the first thing, and you would expect both feet. This is what you would want. You would be looking for a symmetrical type of pathology for foot. Also, it causes a change of shape in the foot, so you'll see foot deformities, high arches, hammer toes, and that's a condition where the middle joint of the toe bends upwardly. Again, very foot-oriented. In addition, lower legs, it may take on an inverted champagne model appearance because of loss of muscle bulk. In other words, you'd have I can't draw, but maybe a thigh here, and then it just gets really kind of skinny, and you have your foot there. Well, okay, that looks like a duck. Well, you get the idea. But that's the inverted champagne type of appearance that you may have. Later in the disease, you may see weaknesses in the hands, resulting in difficulty in fine motor skills. Again, remember, this one starts in the foot and tends to go to the hands later. Some people will experience pain, mild to severe. Again, as I said, it is a collection of genetic mutations. It varies from patient to patient, so it's just not one thing. People think that some of the mutations affect proteins associated with myelin, and in some forms of CMT, there are defects in the axon itself that blocks the transport of molecules in the axon, rendering it non-functional. By the way, the Charcot-Marie tooth, those are 3 different people that worked on this disease. And so I'm just going to point out to you that Jean Martin Charcot, so I'll write the name out for you, Jean Martin Charcot, that he was the first person to characterize multiple sclerosis. So, a little bit of a history there. All right, before I close this section down, I want to make one random point that has nothing to do with clinic, but it's a definitional, because you may run into this term, and if you do, I want you to understand what is being said. One term is called antidromic conduction. Antidromic conduction. And that is where you have the progression of the axon, the direction of the action potential goes towards the soma of the neuron. So imagine that we have, again, that's the soma there. I think you know that, soma, and then here. So this is where you would have the action potential going backwards, hence the word anti. If I were to take a needle and depolarize right there, you would expect the action potential wave to go in both directions, yes? So the direction this way, we would call that antidromic conduction. Okay, so what do you call when it's going in the correct direction? You would call that orthodromic conduction. Orthodromic conduction. So that would be when you would have, again, everything is, action potential is just going down normal. So antidromic, orthodromic. Antidromic going backwards, orthodromic, the conduction is proceeding as normal. Okay, so that ends this little section. For this block, we're going to work through our problems. I think, obviously, if you're doing this via online lecture, which is what we're doing, it would probably be best if you were to attempt the problem, think it through, work it, and then play through my explanation of it. If you just go through here and just watch me do it, you're not getting any benefit from this, so I would try to do it yourself and then follow through. Anyway, but I'm just going to go through these. So in this first problem here, we're putting a potential of plus 45 in an axon. Normal resting potential is minus 70. The axon has a length constant of 2.8 millimeters. And the question is, what is the potential 2.8 millimeters from the point of insertion? Okay, in other words, if I have a membrane, and then I've got, a battery, and then I am putting in that point there, I'm bringing it to plus 45. And of course, if the resting membrane potential is minus 70 millivolts, you're going to have a fall off. And then if it's already been predetermined that the length constant is, 2.8 millimeters away from here, so what would the potential be there? Lots of ways of sorting this out, I guess. One way would be that I've gone from minus 70 millivolts all the way up to plus 45 millivolts. And then I would want to do what is the span of that, with the total there. And another way I could do that would be, say, 45 plus an absolute value of minus 70, and that's going to be 115. So that I know my span is 115 millivolts. Then what I'd want to do is I'm going to say, all right, so what's 37% of 115? And if you remember from middle school or junior high, when you're doing word problems, of means multiply. So 37% of, which means times 115, and that gets me 42.6 millivolts. So, I'm going to be 42, you have 42.6. So what that means then, so that's my 37%, so my reference now is here where I started out, so I'm going to want to go back up 42.6 millivolts, and then whatever that is going to be the voltage at 2.8 from the insertion. And an easy way to figure that out, so minus 70 millivolts plus 42.6 millivolts, and that gets me minus 27.45 millivolts, and that's what that would be, 27.45 millivolts would be there. Okay? Now, one thing just to be aware is that, you can say, okay, well, what if the battery, instead of putting plus 45, what if you just did plus 65? Well, that would certainly also change that, but the length constant is not going to change. In other words, it's still going to be 2.8 millimeters. It's just that when you work through the percentages, you're going to get a different number than 27, but the percentage will still be the same. And so the 2.8 link constant has nothing to do with the particular voltage you put there. You could put any voltage in there, but you run your percentages at 37%, you'll get a different value here, but the percentages are such that it has been determined that the percentage always falls at 2.8 millivolts, 2.8 millimeters from the point of depolarization. So again, the 2.8 is not tied to a particular voltage per se. So at 2.8, the voltage is minus 27 millivolts, but only if I've raised it to plus 45. If I raise it higher or lower, then this number is going to change, but it's still, the link constant is 2.8 millimeters away from the point of depolarization. What you're going to find out is that there's only so many ways I can ask a length constant question. And once you go through the different ways, all questions on an exam is basically the same thing that you see over and over again. So let's do a variation. Suppose you have a cell membrane, has a length constant of 2 millimeters. You put an electric probe into the cell membrane, and the reading 2 millimeters from the point of insertion is minus 50 millivolts. And the normal resting membrane is minus 90. What have you raised the potential to at the point of insertion? So you see what I'm doing on this problem here is I'm changing up what you don't know. So let's draw it out. So I've got a cell membrane. There's my cell membrane there. And I'm going to put, a battery there at some point. And if it's 2 millimeters away, so I've got, say right there is 2 millimeters. Okay, so I want to know what that is right there. So now I've put in some voltage here. I don't know what the voltage is though. So it's some mystery millivolt, but I do know that this is reading minus 50 millivolts and that the resting membrane potential is minus 90 millivolts. So again, I'm just changing what's unknown. And then you solve. Okay, so what am I dealing with? And again, what you're having to do is kind of work backwards a little bit. So the first thing I want to do is see what the change was, from minus 50 to minus 90. And so what I've got here, I can do an absolute value, minus 90, and then minus 50, and that gets me 40 millivolts there. Again, all I'm doing is I'm, in a sense, this problem here is I'm doing this problem here backwards. Okay, so the first thing I want to do is find that voltage there of minus 40. So what that means then is that now what I want to do is, well, let me go ahead and say this for you. Maybe this will help as well. That this value here, 40 millivolts, that is now going to be what this was up there, you see. So, how do I get this? How do I get this? I take 0.37, and on this up here, I multiply by 115 because I was given that. Here, I don't know what this was here, and so therefore, I cannot calculate the equivalent of the 115 up there. So I would go 0.37 times x, and that gets me 40 millivolts. And then I solve for x, and that gets me 108 millivolts. So 108 millivolts is the x here, which is equivalent to the 15 here. And what's the 15 over here? It's the total span. So I went from minus 70 to plus 45. Here, my total span is 108. So I have my start point, minus 90. So I go from minus 90 millivolts and then go all the way up 108, 108. So I'm going up 108 here, and where do I end up? And that's going to be plus 18. So 108 added to minus 90 gives me plus 18. Therefore, and I can go ahead and write this out here, minus 90 plus 108 equals plus 18. Therefore, the potential that I put here was plus 18 millivolts. Now, if you want to check yourself, plus 18, then basically take the plus 18 millivolts and do number 2 just like you did number 1. So again, all you're doing is just playing around with what do you know and what do you don't know. Once you get the hang of it, it's not that bad. All right, so let's move on to some other things here. Okay, here, all I'm doing is I'm just having you reviewing what the sequence is during an action potential. So this is basically something to just to drive you back to your notes in terms of activation gates and inactivation gates of the sodium and potassium. And here we've already talked about that, to be honest with you. Just make sure you understand the concepts on this page. Okay, on this one here, again, I don't think it's that hard. What you have is you have an axon, you have the myelin here, myelin here. Okay, so I've got demyelinated areas here, and here are my roads of Ranvier there, node there, node there, node there, node there. So I've got point A, B, again, these are the nodes, segmented by myelin, but I have some demyelinating event here. So again, making the assumptions here, RP means resting membrane potential. And of course, I got active potential here. So if you're looking at this, and again, think it through and then follow this. What it's asking is point A relative to point C. So I got A and C here. So I'm wanting to know the resting membrane potential at C relative to A. So I've got resting membrane potential at C here, resting membrane potential here, and A, resting membrane potential here. And the question is, with this situation here, what would the resting membrane potential be, A and C? And the answer is the same. Everything's just kind of sitting around being the same. So the demyelination doesn't necessarily affect the resting membrane potential. Then the second question, transmembrane current. So transmembrane current means the current that is crossing the membrane at the node. So transmembrane current at C, which is here, when the action potential is at B. So now I have an action potential here at B, right there. I want to know how that's going to affect C. Compared with the transmembrane potential of current at B when the action potential is at A. So, okay, so what I have here is if I were to have an action potential here at A, then what would the membrane potential be at B? And then if the action potential is here, what's the membrane potential here in terms of bigger or smaller? And the answer to this is it's going to be less. Okay, so let's see why. So I'm comparing the difference between here and here. And so note I have myelin, so I've got a really lovely link constant. So whatever happens at A, I'm going to have a big reaction at B, node to node. But now if I'm at B and then I'm having demyelination here, then can you not see that if I have an action potential at B, the effect on A is going to be less compared to A to B. So that's why you have less there. The action potential conduction velocity from A to D, well, that's going to be obvious, less, because I have demyelination here. And then the action potential amplitude at D compared with the action potential at A, if you could get an action potential, and that would be the same because we're basically saying that action potential is all or none. So that's basically a little exercise to help us figure things out. The explanation to all these is 1, 2, 3, 4, which we've already done. Okay, so I believe the next one is, okay. Consider that we have epithelium transport results in the absorption of food, electrolytes and water from the GI tract. The reabsorption and secretion of the materials by the renal nephron as well is involved. This process uses many of the same mechanisms across their function. In other words, we're transporting things in the GI tract, we're transporting things in the nephron, you're moving electrolytes, etc. One such mechanism is the co-transport of sodium and organic materials, call it glucose, amino acids. And remember, we talked about this in the kidney, right? So we also said that that transport was contingent upon the management of sodium, because when you're pulling in glucose or pulling in amino acids, you are relying on a continuous sodium gradient, and the thing that maintains that sodium gradient is a sodium-potassium ATPase pump. So, suppose that blood flow to a section of an intestine is severely reduced from normal. Predict the effects, increase, decrease, no change of the conditions of the function of the enterocytes on intestinal absorption. Okay, so again, all you have to do is connect that the absorption of amino acids and the absorption of glucose is tied to maintenance of that sodium concentration gradient. So the conceptual leap that I hope you made as you thought about this problem is that if I am shorting the area of glucose, blood, then that means I'm shorting the area of oxygen and glucose and such that now I'm going to compromise the sodium-potassium ATPase pumps. If it's not getting blood supply, I'm going to be short of ATP to run those pumps. And if I'm not running those pumps, then I lose my sodium gradient, and if I lose my sodium gradient, then I compromise my ability for the gut to reabsorb glucose, amino acids, and such. So with that being said, then you can quickly figure out that all of these are going to go down. Okay? So, in real life, I mean, that's the big problem, or one of the big problems if you have an area of blood supply to the gut that's occluded, is you're pretty much going to take that offline in terms of any type of digestional function. All right, so the rest of the problems, these 2 pages here, we'll just kind of go through. Again, using some equations that we have talked about before. So suppose you have a membrane with a sodium conduction of 15 millimoles. If the Nernst value of sodium is plus 58 millivolts, then calculate the amperage of the sodium flow when the membrane potential is at minus 28 millivolts. Well, we certainly have our handy-dandy Ohm's law. And for this situation here, we have a special form of that, and you'll recall this from earlier notes, that the current I is equal to G, the conductance, and now you have the measured voltage potential of the membrane. You've determined that empirically, and then you have the Nernst value for that particular ion. So that's the equation that you would employ. Now, if you did this and you try to stick in, or if this is what happens if you do it this way. So suppose you say, I don't know what the I is, but I know my G is 15 millimoles. I know my EM is 28 millivolts, and I know my Nernst value is 58 millivolts. Okay, if you solve for I, you're going to get the wrong answer. So here's a little trick that you don't want to get snagged in, is that, and you can play with the arithmetic and satisfy yourself that it couldn't be any other way, that Ohm's law, voltage is a product of amperage and resistance, that units matter. And so you have to convert this problem here into volts, amps, and ohms, or mhos. You have to get rid of the milli, or the arithmetic will not work, and you'll get the wrong answer every time. So the correct way of doing this equation would be to say I equals 2.00, nope, too many zeros here. Get rid of that. 0.015 mhos per centimeter squared times minus 0.028 volts minus 0.058 volts. Then when you run those numbers, you get minus 0.0129 amps, which if you wanted to go milliamps, you would go or, it'd be minus 1.29 milliamps. So don't get caught in that. This is something that could be on an MCAT as well, where they throw that to you and they put it in milli, and if you don't know to convert it to regular units, then you're going to get the wrong answer. Now, of course, the question is, what's the minus business for amps? Because amps is just, again, current. The sign for the amps here, it indicates direction. So, you know, plus amp would be one direction, plus amp would be the other direction, but the flow is the same if you're not worried about the direction. Okay? So once you understand this little trick here of making sure you're getting the correct units, then this is really, really easy. You know, it's just basically plug and chug. So let's go with the second one. So you've measured amperage of potassium to be 0.008 amps when the resting membrane potential is 10 millivolts. Nernst value of potassium is minus 85 millivolts. Calculate the potassium conductance in millimos. All right, so what you're going to have to do is convert everything to base units. So I'm going to go 1.008 amps equals G, and this is where I have to be careful because now I go to volts. So this is going to be 0.01 volts minus 0.085 volts. And there you go. And anyway, you work all that out, you're going to get 84 millimos. Okay, I just did some steps, but again, it's just basically plugging in and converting units back to milli. So that's what that would be. Easy peasy. The next two, again, pretty much it's the same problem over and over again once you know the trick. So we'll go through this real quick. So this is going to be 0.0085 equals 280. And then you have, in this case, the resting membrane potential you don't know, but you know the Nernst value, 7.5. And let's see, that's what you don't know. When you work all this out, this ends up being 0.031 volts, which is 31 millivolts. And the last one. And again, plug and chug. Make sure you get your units right. A lot of zeros here. 0.0004 amps equals to G minus 0.07 volts minus 0.128 volts. G is going to equal to minus 0.002 mhos. And again, you got to make sure that you're answering the question being asked. They want to know what is the resistance. And so if you do the inverse, that equals to minus 495 ohms. And again, the negative, don't worry about that because, again, that has to do with direction. So resistance is a resistance. It's just the negative is a directional function. Anyway, that's basically how you handle these active potential equations. So once you get the hang of it, there's just no reason to miss any of that.